I'm Dr. Sori. I got it. I'm Dr. Sori Gomisai, Associate Professor in Physics in Al Faisal University. So actually, I have changed a little bit my title in order to make it more exciting, especially for photovoltaic applications, and mainly for the new, the recently well investigated inorganic mixed halide perovskites. So for the introduction, I wanted to say that actually we are thinking, especially here in Saudi Arabia, actually since 10 years, we have made the plane, national plane to switch to more renewable energies and clean energies, green energy for environmental, let's say friendly environmental, and mainly wind. We're having also solar energy since like let's say 70s now. They started with the first generations, etc. And the situation is like all research now are oriented to renewable energies and mainly solar energy. So my background here is like I'm using computational material science approaches to work on to investigate potential materials for solar cells applications. So we started with basic semiconductors, made their nanostructure, thin films. We used also, or we studied also the thermoelectrics, and now since now let's say maybe 7 years now, we're having collaboration with experimenters here in Saudi Arabia and actually abroad, to work on more oriented perovskite systems. So the idea is actually is like to look for also cheaper materials, easy to make, available in order to let's say overcome the problem of the efficiency. So we know that solar cells are the target of solar cells is to let's say convert solar energy to electricity. And actually I can show you, for example, here, this is the chart, I think the recent one, where actually anyone working in solar cells is looking for. So if I can talk about myself, maybe I started with the really semiconductors, let's say basic ones, silicons, etc. Then moved to more alloying, like 6 and materials based on cadmium telluride. And when I was in Georgia Tech, we were working also in organic photovoltaic. They were, let's say, we still have limitation or limit on some problems with the lifetime of these systems. And now we have more emerging systems like perovskites, and we are reaching around 2025 recently for the efficiency. So this lecture, I will show you my recent work here. Yeah, so here is just to show like, sorry, we have here typos, alkali halides, perovskites, how they are, the form, etc. We have the organic, we have the inorganic, we have the hybrid organic, inorganic. We're working on them all from, let's say, theoretical computational point of view. And here is the recent work we did. It's based on cesium, lead, iodine, and bromine, of course. So here what we did, it's like we started from CSPBI, actually the iodine, cesium, bromine, and we tried to make some alloying by, let's say, doping with sorry, here Br, so the bromine, to dope with iodine in order to change the structural, so the electronic and optical properties. And here are the structures. So from, let's say, the parent. So we always see here the parent and here the second parent, and the alloying by changing the concentration of doping, mainly here iodine. So here it's CSPBI we doped with brom. So we started changing the concentration, let's say from zero, with interval from 0 to 1, with an interval of 0, 1, 62. And actually, it's like we're putting 2 bore every time. The story with this is like experimentally, this let's say changes in structure where okay. This presentation, sorry, the alloying was made experimentally, and it was reported in different references. I'm putting the references here, and so we start with the structure, and actually my work is based on density functional theory. So it is DFT, so ab initio, first principle calculations, which means the solution of quantum mechanics Schrodinger equation. And here we we have plenty of softwares. We're using QuantumWise, we're using V2K, VASP, CASTEP. With this work with my student, we used CASTEP. So the idea, the basic idea for people who are not familiar with let's say with the DFT calculation is like to start by relaxation or geometry optimization. So the geometry optimization aim to to find the minimum energy, so to minimize let's say the energy and get the optimized structures. So we did it for all these structures in order to have them optimized. Then after that, so here it's like I'm showing the summary of calculated equilibrium volume. So for each structure we calculated the equilibrium volume. It's like the volume of our structures and the cohesive energy. Of course, when we compared them to the experimental data available one, we have like disagreement of 3.80%. Means that roughly we are, let's say 96% in agreement with experimental data we have, which makes sense because actually there is always something different between theory and experimental data, because we cannot reproduce let's say the experimental results. But actually this is a good let's say starting for DFT calculations. So also you can see here that we have negative cohesive energy, which can lead us to understand that those structures generated, like hypothetically speaking, when respecting the symmetry, are stable from structural point of view. So the idea is now after, let's say, doping with bromine, and here you can see all the concentrations. So this is the parent 1, the parent 2, and these are like the variation of X. So you can see it here in the structure. X, we're changing X by 0.7033 until having like 1, 2, 3, 4, 5 intermediary structures between the parents. So the parents are here and this one at the end, okay? So after that, so once we have this structure here, I can show also the volume versus the bromine concentration X. So it shows that like there is a systematic change of lattice volume. It's like quadratic equation. So we're getting this with the polynomial fit using origin. It is like fitting all the, let's say, behavior that we can observe when we are starting with 2 parents and doping, doping with different concentration. We always have this behavior between 0 and 1 concentration, okay? Another important thing also was like to see the material stability, because actually this is something like sometimes we are not comfortable with regarding theoretical work, especially DFT, when we are doing like hypothetical situations or hypothetical methods or materials before making them experimentally speaking existing. It was always the problem of the stability. Can we make those materials stable, even dynamically, from phonon point of view? So here we have calculated the enthalpies or formation enthalpies using this formula. So it's like we followed the interaction here, the chemical reaction, sorry, between CS X and PBX to get our CS PBX. And then what is happening is like we calculated the enthalpy here for different concentration. Of course, the data we're getting them from, of course, DFT, and for each concentration we calculated the formation enthalpy versus the changes in the bromine concentration. What we can say here, we can see, actually, with the increase of brom and let's say bromine concentration, the enthalpies is increasing. Increasing, but actually decreasing in the sign negative, so it is more stable. So our structures, we can say that they are relatively stable here. Again, another thing also most important after checking the structural stability is like to calculate the electronic structure. So here for the electronic structure, it's a big debate in DFT because we know all the difficulties where DFT is underestimating or overestimating sometimes the band gap. And we know when we are dealing with the materials for solar energy and photovoltaic, the band gap calculation is very, very important. So sometimes we need to, let's say, try different approaches. So I can say here about like we have LDA, GGA. Maybe I'm saying things like this, but they need more like more explanation. Hybrid functionals. And here we used the meta GGA. So it has ability to, let's say, correct the band gap calculated with the classical GGA. So what we did, we calculated for each structure, actually from the parent one, the parent two here, and between them for all the concentrations of the bromine, we calculated here the band structure, and also we are displaying only the most important Brewin zone, X, gamma, Y, and mainly gamma is interesting us because this is where the valence band maximum is reached. So basically what we can say here, okay, we are having semiconductors. The band gap is also fluctuating, I would say, with the changes of the concentration, which means that we can tune here the applications. We are targeting photovoltaics, so we can know which concentration we want to reach in order to get the right band gap for different applications. So it's like we started with 216 volt here, around 216 volt. You can see it here. And we are around, at the end, I can give you the, so with the doping, we started decreasing the band gap until reaching 175 electrovolt. So the bromine is decreasing the band gap. 216 is too much for photovoltaic. 175, actually, the ideal band gap is 1.6. So reducing the band gap of these materials is really important to make it available or easy for photovoltaic applications. Of course, it is something that's very important here is always to check if our results are reproducing or approaching experimental results. We have actually checked that for some experimental data that have reported 173, 182, 232 for CSPBI3 and BRT respectively, which means that like even experimentally we don't have fixed value. It's still fluctuating and it's dependent on the experimental condition, but our results are in the same interval from the experimental results. One important thing also here is like we have considered the spin orbit coupling. Why? Because actually we have heavy elements like PB in general, where we have the lead, we need spin orbit coupling correction, and it is also correcting the band gap. Usually it's under, reducing it. Okay. So here, like, and this is something like a routine that any DFT people will do, is like to check the variation of the band gap versus the concentration. And here we are reporting it for with and without spin orbit coupling, of course. And you see here how the spin orbit coupling is reducing. And actually, it's like reproducing the band gap more, let's say, efficiently than without spin orbit. So it's important to have the spin orbit, and we can see here the behavior of the band gap, how it is fluctuating versus X. So this quadratic equation is very important for any experimental in the future, and we can do it. We can extrapolate this routine to any other alloys. Of course, we calculated also the effective masses. In general, effective masses also measured experimentally. And actually, we did it for the holes and electrons, I mean, for the charges here carried. And actually, they are in, let's say, in the same order as this perovskite here, MAPBI3. And this is the famous one. And actually, this is like the head of the family on these materials based on lead and bromine. And actually, I have a lot of work on it, experimentally and theoretically now with students. And it is at least in the same range as this perovskite. Of course, experimentally, it was reproduced the same thing. So at this stage, we are just showing actually that our DFT is approach is really working fine in reproduction of the structural stability, electronic structure, and also the effective masses and all derivative, I mean, all related properties to the electronic structure. Before I conclude this talk, we have the most important thing is also the optical properties, because from the optical spectra, we can know where the semiconductor is absorbing or reflecting. And actually here we calculated the the dielectric functions. Of course, epsilon 1, epsilon 2. Epsilon 1 is the real part, epsilon 2 is the imaginary part. And there is no surprise actually, because actually the optical properties is just more meshing, let's say more restrict, more criteria on the convergence of the DFT calculation, mainly the key points. And it is always reproducing the electronic structure. So the dielectric constant here is we're calculated for all concentration, of course, and it is intermediary step here. Intermediary step because we can get also the most important one I can show you here is the absorption coefficient. So the good thing here, I have colored for each, let's say, concentration, the changes in the absorption coefficient, and you see it's increasing. And actually, it's also reproducing the energy band gap, of course. Now, the good also, the news here, of course, we are absorbing in visible spectra. So this is something very important. Here, alpha, omega, the frequencies, so omega is 2 pi f, are the formula that we used to extract the absorption spectra versus energies from the dielectric constant here. Before this, we have plotted here the static dielectric constant, which means that like this is the dielectric constant at E equal to 0. It's something very important, and it shows that there is linear change or decrease when of the static dielectric constant when the bromine concentration increase. So what we can say again also about these materials, they have a high absorption here, so it's around like with a arbitrary unit or the unit of the absorption coefficient. They are in the same range as other materials now well known for photovoltaic applications, CDT, so cadmium telluride, and it shows that like DFT is reproducing the optical spectra. Before I finish, I think we have here a summary. So DFT, we use split potential plane wave, which means CASTEP. We are repeating the calculation with the other softwares and with the more efficient, let's say, approximation like the hybrid HSE06. The electronic properties and light absorption characteristic of black phase, and actually we call it black phase gamma, because actually in cesium PBI Bohr, we have perovskite, we have different phases, alpha, beta, and this one is called black phase gamma. They are stable. Actually, they have attracted the attention of the photovoltaic community in 19 and 20, 2 years ago. So this is why it was this work was published in Journal of Alloys and Compounds in 2020. And it shows like the changes, or let's say the tuning of the structure of the parent CSPBI with the bromine is making the material more stable, enhancing the stability, and also decreasing the band gap to make it, let's say, adaptable for photovoltaic applications. So we are trying now, because the debate is still here about the band gap. And actually, when we are working on DFT and mainly for photovoltaic applications, it's always the debate on if the band gap is correct. One thing. The second thing, some structures are not always synthesized or existing realistically. So we are trying to look for more stable structures. I can share with you the recent maybe work, like I didn't report it here, but we are trying to use the machine learning by tackling a huge family of these materials and putting criteria on the stability, which means the formation enthalpy and band gap, and like like analyze these two criteria on different perovskites, inorganic, organic hybrid perovskites, in order to see which one we can pick from this family and make it, let's say, available, or I mean, make it reproducible experimentally, and also can give good performance in photovoltaic. Of course, after DFT, we're trying to take the device, because this is what is happening. It's not always the bulk materials we're having devices. So we have different approaches, let's say multi-scale approaches using DFT calculation, and other based on green functions, like transfer properties. So sometimes we take those materials, we build the device and get the efficiency. Sometimes we make it also in what we call semi-analytical approaches, like the SCAPs. And we try to get also build a device, get the back contact, everything like the solar cells, and see how the efficiency is increased or decreasing, depending on the tightness, or on all, realistically speaking, parameters of solar cells, you know, doping, charges, Curie concentrations, all the conditions. So DFT here is always the first step for us. So this is why I just like shared with you this work, and this work is in progress with many other materials. And as I told you, now we're using artificial intelligence, machine learning mainly to tackle huge families. We have now access to data in materials today. We have banks now online. Sometimes we use them, we calculate them by ourselves. So the project is really viable, and actually it's attracting a lot of attention, and we're happy also to have other publications in good journals like Solar Energy, Materials Today Energy, etc. So yeah, just to share with you some of my recent work, and thank you for hosting me. I finished.
From the beginning.
Yes.
Oh.
Hello everyone, I'm Sixun Gao, and my topic is high-speed multi-format digital encoding of silicon pin junction waveguide modulator. And my advisor is Dr. Gonglu Li. First of all, this is my outline. The introduction part will first introduce the criteria of the data center, then silicon photonics integrated circuit and the historical review of silicon Marzender modulator. And finally, my motivation. Then I will introduce the basic characteristics of silicon Marzender and the transmission performance of OK and PAM4. The second section is the transmission performance of silicon Marzender encoding OFDM and the pros and cons of single drive or dual drive. Finally is the conclusion. In order to meet the huge computing needs of future data center, in 2017, IEEE formulated 400 Gbps specifications for short distance and long distance transmissions. In order to further reduce the number of transmitters used, in 2018, MSA further defined FR4 and long distance transmissions. The LR4 specification enables a bit rate of 100 gigabit per second per channel. The mainstream method for long distance transmission in the data center is to use EML external modulators with single mode fiber transmission. In order to meet the next generation of 800G and 1.6T, for the high transmission bit rate, the single channel 100 gigabit per second requirement is necessary. Next, I would like to introduce the development of silicon PIC in recent years. Dr. Rick Mann, CEO of Rockley Photonics, once said, nowadays, the industry development is getting crazy. Moore's law is getting harder and harder to achieve, and it's getting harder and harder to reduce costs. But if we're using the right materials to do the right combinations, we can break this law. As everyone knows, Moore's law predicts that the number of transistors will double every 2 years. However, in recent years, it has become more and more difficult to achieve the prediction. However, if you switch to silicon photonics technology, you can see from the upper left and lower left pictures that silicon compartment can be made smaller more tightly. Therefore, the advantages of silicon Marzenders are: first, it can break through Moore's law. Second, it has lower loss. Third, it can be made smaller. Fourth, it can be applied to short or long distance transmissions. Fifth, in addition, the cost is relatively low. The application of silicon photonics includes thermal optical modulation, electro-optical modulation, or optical modulation, and or optical logic gate. Then I will introduce the silicon Marzender of p-n junctions. Its operating principle is mainly to apply reverse bias on the optical path of the Marzender to change the refractive index and phase, resulting in intensity modulation. There are 3 parameters that mainly affect the performance. Respectively, there are p-n junction operation, impedance matching, and transmission loss. The silicon Marzender of p-n junction mainly has 2 modes of injection and depletion. The advantages and disadvantages of the injection type and depletion type are listed in the table. The injection type will inject the Mayer carrier into the p-n junction. It can reduce its power consumption. But there are also problems of transmission loss, lifetime, and bandwidth reduction. Under depletion condition, carriers will be discharged, so the loss and lifetime are small, and the 3 dB bandwidth is relatively high, but V pi L and power consumption are also larger. And using PN junction has several advantages. For example, it has lower chirp, higher transmission bandwidth, and long distance transmission. Next is the historical review of silicon Mach-Zehnder. In 2012, a research team used the injection type silicon Mach-Zehnder to achieve V pi L 0.29 voltage times centimeter in a differential manner, and the 3 dB bandwidth is 7.89 GHz. In the case of back-to-back, the data rate of OOK is 12.5 gigabit per second. In 2015, other research team used hybrid silicon Mach-Zehnder and switched to a depletion mode to increase its 3 dB bandwidth. And the transmission performance of OOK through 2 kilometer single-mode fiber is 56 gigabit per second. In 2019, a more research team designed a dual-arm silicon Mach-Zehnder which transmitted 40 gigabit per second OOK and 80 gigabit per second PAM4 through 10 kilometer single-mode fiber transmission by depletion type and in differential operation. And this page is the experimental setup. OOK and PAM4 are generated by AWG as the data format after the signal is amplified. BAST inject DC and RF into the GGB probe. In the experiment, we use two types of probes. The GSG probe on the left is used for modulation, while GSG is used for impedance matching. The optical path part, the C or L band light source is generated by tunable laser after EDFA and OBPF for amplify and filter. And it enters the silicon Mach-Zehnder for modulation. The optical fiber is 2 kilometer, 10 kilometer single-mode fiber and 2 kilometer and 10 kilometer dispersion shifted fiber. After the fiber, it is received by the receiver and converted into electrical signals, and then enter the OSA to observe the eye diagram. Next, I will introduce V pi L product of single-arm driven asymmetric silicon Mach-Zehnder. The above figure shows the transmission spectrum of the silicon Mach-Zehnder from 0 to 4 voltage. The FSR is 14.73 nanometer, and the overall delta lambda is 6.48 nanometer. From the formula, we can calculate that delta phi is 0.88 pi, and the V pi L from 0 to 4 volt is 0.909 less delta phi which is much lower than the standard value of 1.7 voltage times centimeter. In addition, the following figure records every 0.5 voltage, delta lambda, delta phi, and V pi L. It can be found that as the base voltage increase, V pi L increase nonlinearity. The reason is that when the base voltage is applied, there is another carrier plasma-induced dispersion effect that will cause the refractive index and absorption. Therefore, the base voltage changes. The depletion is different, and the refractive index will also change. Then consider the modulation efficiency and linearity at different wavelengths. We measure its LV curve and the differential type slope. From the LV graph, we can see that as the wavelength increase, the ER increase, and the modulation, the smaller the required amplitude, the smaller the relative required power consumption. From the dP/dV diagram, it can be found that increasing the wavelength will increase the slope from 0.8 to 1.4 millivolt per watt, including that the increase in wavelength will lead to nonlinear modulation, and the signal distortion can be summarized from the analysis of the above two figures. Although the increase in wavelengths can reduce power consumption and increase the modulation efficiency, it will also reduce the linearity of the modulation and cause the signal to be distorted. And this page is reflection of impedance matrix terminator. The next thing to discuss is the impact of impedance matrix. The two pictures on the left are the result of measuring S11 and VSWR with terminators of different bandwidths. When comparing 20 GHz and 50 GHz, it can be found that when 50 GHz is used, S11 drops from -4 dB to -27 dB, and the VSWR drops from 6 to 1.1, which means that the use of high-frequency terminator can reduce the reflections and standing waves caused by reflections. The basic characteristics change of silicon Marzender with and without terminator are sorted out in the table. It can be observed that the terminator is added. The resistance value is close to 50 ohms, and the reflected power is reduced from 99% to 4.9%, and the 3 dB bandwidth is increased from 11.7 GHz to 33.3 GHz. This shows the importance of impedance matching to the transmission signal. In order to further understand the response of the component and the terminator, the response of the silicon Marzender after impedance matching with different bandwidth terminators and the response of the bias voltage of 1 to 3 voltage are measured. From the first picture, it can be found that high-frequency terminator is used for impedance matching. It can make the response flatter and increase the 3 dB bandwidth to 33 GHz. From the second picture, it can be observed that the higher the bias voltage, the better the flatness of the response, and the 3 dB bandwidth is increased to 34 GHz. Because the higher reverse bias, the less the carrier in the PN junction, thus improving the 3 dB bandwidth. This page is about the Marzender chirp and single-mode fiber dispersion compensation in silicon Marzender. In order to understand the chirp of Marzender and the dispersion caused by single-mode fiber and dispersion shifted fiber, we measure the chirp of Marzender and simulated the power attenuation after transmission as the formula. The upper left figure measured the chirp of Marzender is 2.73 GHz, which can be determined by the formula. The chirp parameter is calculated to be -1.76. And substituting the the dispersion of single-mode fiber and dispersion-shifted fiber, the conditions of 2 kilometers and 10 kilometers can be simulated. From the figure below, the power attenuation of 2 kilometers single-mode fiber is not serious, but the power fading dip of 10 kilometers single-mode fiber happens in 26, 38, and 48 gigahertz. After 10 kilometers of dispersion-shifted fiber simulation, the first-order power fading was delayed until 58 gigahertz, indicating that the power fading caused by fiber dispersion can be effectively suppressed. This page is about the principle of preemphasis. The technology of preemphasis for the phase and amplitude precompensation. First, the broadband signal is used to obtain the channel response of an entire system, and the AWG obtain the channel response to make OOK or PAM4 signal predistortion. The predistorted signal can effectively compensate the originally measured channel response and further improve the power decay at high frequencies to optimize the overall transmission performance. This page is the summary of the section 1. The left is the summary of the first section. First, from the basic characteristic measurement, we get a V pi L 0.909 voltage times centimeter, lower than the specification. Second, in the impedance matching process, it is found that the use of a 50 GHz terminator can effectively reduce signal reflection and increase the 3 dB bandwidth to 33 GHz. Third, in the chirp measurement, silicon lavender only has a frequency chirp of 2.7 GHz, which can reduce signal distortion. Fourth, DSF can suppress the impact of power fading, but more mismatch also cause an additional 0.7 dB loss. And finally, the transmission part. From the table, it can reach 100 gigabit per second PAM4 over 2 kilometers single-mode fiber and pass the inter-data center FR4 criteria, and under 10 kilometer transmission, it can reach 50 and 52 gigabit per second under both OOK and PAM4 data format, which can pass the LR8 criteria. Next is the basic characteristics of all band. The above figure shows the transmission spectrum we measured from 0 to 3.3 voltage. The FSR is 10.25 nanometer and the delta lambda is 6.48 nanometer. In addition, it can be found that the operation performance of the two arms is not much different. The best operating point is not so intuitive. So the next page, I will start to introduce the use of PV curves to find the best reverse bands of each arm for dual modulation. This page describes why dual operation is not used in C-band because it is difficult to find a suitable modulation curve. It is hard to find a symmetric two lines, and we use O-band as our light source to avoid the power fading caused by fiber dispersion. We will discuss the PV curve in next page. This page shows the PV curves of left arm and right arm in op-amp. It shows the picture of power versus reverse bias operating from 1306 nanometer to 1309.5 nanometer for single arm drive. To realize dual arm driven operation, the modulation curves of the left arm and right arm should be upside because the two input signals are upside, which exert on the right arm and left arm respectively. Therefore, it is necessary to select the operating wavelengths for both the left arm and right arm of the PV curve to be symmetrical for dual arm driven operation. The more symmetric the two PV curves, the better the modulation efficiency of dual arm drive. Even the two PV curves are quite symmetric. The appropriate reverse bias applied on the left arm and right arm are not the same because of the asymmetry of the two arms. The reason for selecting 0.08.5 nanometer as operating wavelength instead of 1310 nanometer is that it can avoid operating at high voltage. In this work, it is essential to find a suitable wavelength for a symmetric silicon modulator based on selection criteria of symmetrical modulation curve and low reverse bias. As the total voltage of the two arms rise, the crossing point moves to a high voltage. Appropriate control of the voltage of the two arms can adjust the equivalent modulation curve and reduce its power consumption. However, if the voltage is too low, the transmission result will be affected. The reason is that the voltage difference between the two arms is too large. The arm at low voltage is affected by the other arm at high voltage, and the modulation curve from 0 voltage to 0.3 voltage will be affected. Single arm modulation originally needs to select the wavelength, but you can choose to adjust the voltage of the other arm to change the PV curve instead of selecting the wavelength. Dual arm driven in the 16 quantum OFDM signal format from 0 to 20 GHz SNR performance is better than single arm driven, but after 25 GHz, the SNR drops sharply. The reason is that the frequency response of the two arms are different. In the 4 quantum OFDM signal format, the SNR of dual arm driven drops sharply above 25 GHz, while the single arm modulation can be maintained to 33 GHz before there is a significant decrease. Dual drive has better performance at low frequencies, but as the bandwidth increases, SNR degradation is greater than that of single drive. Increase to 16 quantum OFDM. The allowable bandwidth of left arm driven is 32 GHz. The allowable bandwidth of right arm driven is 33 GHz. And the allowable bandwidth of dual drive is 31 GHz. Compared to the data format of 4 quantum OFDM, the allowable bandwidth of all operation modes are pretty close. But the SNR of 16 quantum OFDM is similar to the SNR from previous page. The SNR of dual drive falls sharper than that of single drive due to the asymmetry of the two arms. In this page, we can see for 32 quantum transmission, whether it is single undriven or dual undriven, the allowable bandwidth is reduced due to the higher SNR criteria. The allowable bandwidth of left arm driven is 25 gigahertz. The allowable bandwidth of right arm driven is 28 gigahertz. And the allowable bandwidth of dual arm driven is 27 gigahertz. We can see that impedance modulator always cause the phase error for any normalized output transmission, but it's more significant for small output transmission. This indicates that M-quant implemented in future systems will be affected much more significantly by unload impedance than QPSK of current systems. Since M-quant has constellation symbols with small normalized amplitude, which also need process phase control. It was suggested that M-quant with large M for advanced systems should have more extinction ratio to about 30 dB for tolerable phase error. This page is the summary of section 2. Considering the lack of time, here are a comparison table of single drive and dual drive through bay-to-bay 2 kilometers single mode fiber and 10 kilometer single mode fiber. Considering the power consumption and the requirement of setting up the system, single undriven can do better than dual undriven. If the process error between the two arms can be reduced, dual undriven can perform better than single drive. Single drive, in the case of a selected wavelength, single drive has less selectivity in adjusting optical power and signal amplitude than dual drive. Single drive requires a trade-off between single signal amplitude and linearity. Dual drive performs better at low frequencies than single undriven, but the price of doubling the signal amplitude is that the signal has time delay. It is more difficult to select the wavelengths and operating voltage in the initial stage, and the two arms have higher requirement for the process. However, dual drive can solve the problem of insufficient linearity in single arm modulation and resist SNR degradation caused by long distance transmission. Here is the end. This is the end of my presentation. Thank you for your listening, and I hope you all enjoy my talk.
So first of all, I really would like to thank Gil and for this Laser Optical and Photonic Society, especially Sarita ma'am, who actually contacted me via LinkedIn, and gave me this opportunity to talk over here. So let me just okay. So this talk is I'll be trying to cover up a part of my vision because I'm currently pursuing my PhD, and some of the review that I did on my problem that I formulated. So regarding this vision that you see on the just right side, this has been recently published, just now got acceptance in SPI Optical Engineering and will be online soon. So let's jump into it. So this is the group that I'm part of at Punjab Engineering College, and it's a small group, but as we are same level, Mr. Kamna Kohli, she is working on optical fibers with at INST Mohali, and me working in integrated optomechanics. Then Mr. Jeevan Jot Singh is working on all optical networks, on-chip networks, and Jasjot Kaur Sohota, she's JRF working on fiber Bragg gratings. So let's jump into the thing. So when I talk about integrated nanophotonic infrared sensors, the previous task was very, most of the talk was very well explained by the things, and most of the work we see are concerned with data communication, and word is actually concerned with data communication. But again, the very important part is, you just can't take it as take it for granted that the data collection is also an important part. If you do not have data, you won't be able to process. You have nothing to process. So to process that data, you need to have so much of data, and infrared sensors are one such thing which actually are now enabling a lot of data for users, especially after the pandemic scenario. We have already seen that. So this is a very quick summary that it is a study of light and its interactions with matters at nanoscales. And the future of sensing, this actually lies, what we actually need is, till now most of the literature that we see is actually either sensors working for a particular peaks, and then they have so much losses because of, again, the Moore's law limitation in the electronics circuitry. And the moment you convert your photons into electrons, so most of your energy gets lost into the substrate because of the lattice mismatches, free carrier absorption. So this is a very good vision presented by this Mai Yiming in 2020 that actually motivated me to pursue this research. That could lead to high-speed integrated circuits, night vision for defense and commercial vehicle navigation. Once this vision is accomplished, you could actually change the world. So when I talk about particularly what I'm looking for is Midway Ir Sensing. That actually something when you go beyond your 1.55 C-band telecommunication, you go beyond 2 micrometer, 3 micrometer, because that is the region where most of the black body radiations are concerned with. So detecting those thermal infrared radiations, which are actually above room temperature, is a concern. So those wavelength peaks are actually 3 micrometer, right, within this band. Now, this particular thing, if you find application in various, object detection in military, and biosensing or smart sixth sense technologies are coming into picture, then on the bottom left, bottom right, you see you have the hyperspectral imaging from the satellite. In fact, in ISRO has just launched, 3 years ago, a hyperspectral imaging satellite in the payload. So the idea is, you need to have a multispectral photo detector, which actually currently state-of-the-art technology is very costly because of certain reasons we'll see. So what happens is, whenever light interacts with material, the phonons are generated. Now, what are these phonons? We need to understand this. So phonons, just like the photons, light energy is printed in photons. So when they interact with matter, the lattice vibrations led to scattering of this photon energy into a different momentum. So due to this, the phonon is actually, this is related to the frequency of vibration and the temperature. So if the temperature is raised, amplitude of the atomic vibration increases, and quantum terms, this is considered as an increased in number of phonons in the system. So the idea is, what happens is, till now at C band we ignore this phonon energy. Why? Because the energy of the photons at lower wavelength is much larger, as E is equal to hc by lambda. So as the lambda grows, energy of the photon goes even lower. So you just cannot afford to lose those phonon energy, scattered photon energy. So you need to conserve these phonons, right? So this is just a graphical user interface that shows you, that phonons take a finite amount of decay time before it is actually thermally relaxed. So thermal relaxation time is an important parameter of consideration. So within that, actually, we need to convert those photons into electrons, right? So, such a distribution of energy of phonons in longer wavelengths is actually, very critical, especially at mid-wave IR and long-wave IR, because there the photons are already of very low intensity values. So you need to conserve this phononic law. This is the very important need of the hour. especially when you go on chip. So the problem is this thermal relaxation time is inversely proportional to thermal conductance, right? Now the thermal conductance is a material property and hence is specific to a particular material. So a suitable material with lower thermal conductance is the need of the hour, right? To go on chip. Now, another problem is that small thermal conductors of sensing material put a limit on the sensitivity of device because the detector response gets slowed down. Now, therefore, this trade-off between having a large thermal relaxation time and the multispectral sensitivity is again a question, a challenge actually. So the research community across the globe has come up with two broad solutions to this problem. One of them is synthesizing the thin films of 2D materials, which you would find a lot of literature in the market, right? Going from you have HPN materials, MOS2, CRO2, graphene waste, and vanadium oxide, right? And now some of the leading two-dimensional materials that you could see is one of this work by Wiley in 2016. Another one, this one is a part of a group at Nano Research Lab in our institute, Punjab Engineering College, by our senior Shaunak Bansal, 2020. So the problem with these kinds of materials is the complexity and the cost factor in synthesizing these thin film materials, though their efficiency is very, very good, right? But the high sensitivity over a wide range of wavelengths is still needed and still need to be achieved. Now, the alternative solution to this problem was demonstrated almost a decade ago simply by insulating the substrate and other colder contacts with dielectric membrane and for sensing. Now, this ended up having an emerging suspended waveguide platform that, that is just the state of the art right now for achieving low loss on-chip photonic device since last decade. So people have been working on this, like the Richard Soref. I actually got motivated by this person's paper when I started reviewing my PhD work in the first year back in 2018. So it says that benefiting from the thermal isolation to prevent decaying of vibration energy to bulk, that could actually help get on to a strong light matter interactions over infrared, especially the longer one. So this was the work that he, in 2006 presented, where he just tried to suspend the this waveguide. He etched down the silica beneath the silicon, and he actually achieved some good results in terms of cost parameters. And this actually then followed by a series of theoretical and experimental investigations, and especially over shortwave IR ranges till 2.4 micrometer. So this definitely has proved its potential. Especially in terms of examples like on-chip waveguides and cavity-based coupling. And the matter of fact is that convincing approach to replicate this technology for multispectral sensing is yet to be developed. Again, no doubt this is just the beginning, and later on the people are trying to go multispectral. Why? Because for each and every application you need to have a different photodetector or sensor, so that increases the cost multifolds. So for that, we'll be reviewing some of the important material platform, germanium and silicon germanium. So the incident photons, we have already mentioned that they lose energies in terms of photons. So at longer wavelengths, such scattering losses become highly nonlinear. So the nonlinearity actually coming into picture over here. So the goal is to have a very strong on-chip coupling, and that can be achieved by controlled nonlinear interactions. And when I say the word controlled nonlinear interactions, here actually I mean by controlled dispersion engineering of the material. So materials is one of the very crucial factor over there. So one of the third order nonlinear effect that becomes prominent over Midway IR is stimulated brilliant scattering, right? And so now that we know about phonons and photons, so it's time to talk about on-chip interaction issues in the conventional sensors, right, over MWIR. So some of the issues are, the first one is midwave IR sensor coupling issues. So what are those? Like weak phonon and photon coupling at longer wavelengths. Why? Because high scattering losses due to uncontrolled nonlinear effects, and this actually poses a problem for external cooling required for room temperature. Because of this thermal loss of phonons, you need an extra cooling circuitry for your photodetector to actually work in the room temperature environment. So for this, this can be have two types of nonlinear effects, which are third order nonlinear effects. Raman scattering is very prominent one, and the brilliant scattering. And the Raman scattering is actually due to molecular vibrations. So frequency shifts only in one direction, and it's very good for fiber-based sensing and higher optical power threshold. While SBS is a scattering that occurs due to phonons of the acoustic frequency and the scattered photons. So the frequency shift that you observe, usually maximum is in backward direction. That is the good point for cavity-based devices. And it reduces zero in the forward direction. That is a good point for fiber-based communication. So unlike your SRS, your SBS can be good for both type of fiber as well as on-chip waveguides, but with the condition that you need to do a very controlled dispersion engineering. So to make sure that the optical power threshold, because it is giving you a very lower optical threshold. So that is why people are utilizing this concept for ultra cool lasers, in fact. And since it has a narrow gain bandwidth also, so this is another reason that people are using it for ultra fast lasers and ultra cool lasers, right? So when I talk about external cooling mechanism, if you do not cool down your conventional sensors, you might end up getting your actual image, where on the right side you want this as actual image, but you will end up getting the one on the left side, right? So uncooled one, and when you put on the when you cool down the camera, then you actually get your desired image. The idea is to constructively couple the phonons captured in the low intensity. So the recent devices that have been put, I'll try to bring them. So this is the new research, because you are trying to engineer the dispersion relations of photons and phonons simultaneously. That is why this name has been given when I started my PhD journey by a person. So this has been called as another given to Photonic waveguides, because it is a combination of photons and phonons, or also popularly known as optomechanical crystals, right? So one of them is the photonic crystals. So we need to understand the big picture. The big picture is you need to have a low power and multispectral operation. Then how it could be done? Suspended waveguide structures, bringing nanophotonics with photonic crystals, plus the advanced 2D materials, very tedious to synthesize. So you need to choose which approach you want to go. So the third, finally, you have the photonic crystals. You need to do the engineering of electromagnetics and elastic waves together. So to solve the coupled wave equations for those. So conventional platforms have been reviewed. So I'll try to quickly go because we have limited time. So this was the some of the work of the silicon platform, where you have just the substrate, above it you have the undercladding, and then you have the rich waveguide. And what it shows is some of the pros of this, most mature platform with commercially available substrate. But the problem with this is, I want to highlight over here, is this require non-standard processing to create vertical index contrast, such as freestanding configuration. Then you have very low mechanical stability with this, supported pedestal complicates. So again, even if you are somehow achieve the stability of the mechanical, then the broadband spectra is very limited, so it is bandwidth limited. If you are just using it as a chemical sensor, go for this platform, very good. But if you are going for a broadband application, you need to find some other solution. So some more works you could find in the literature. I'll quickly go through this. And I have actually, and then finally, next thing was that people started to do the edge, right? So just removing the air clad, the undercladding that we saw, then this person removed this and observed even better confinement of the modes that you see over here at 2.7, 3.2 micrometer. And that too at a loss of 3.7 micrometer. But now the thing is, the loss is still too high, 2.5 dB per centimeter. And although this platform didn't prove very successful, however, it is worth mentioning in this thesis because it falls midway between conventional and non-suspended and suspended. So we have just the midway between our journey right now. So next thing is conventional germanium, because we need to shift to the Midway Ir platform, right? So again, continuing the legacy of group 4 things. So the major works in the literature you could find is germanium on silicon, germanium on nitride, germanium on insulator, germanium rich graded silicon germanium platforms. And some of the consequences you can see is for the germanium on nitride, although it's giving you a very good contrast between, that is benefited from the compactness of the device. The banding losses are very, very low. But the problem over here is still the loss is very high. Again, we are running for low loss and the high sensitivity. So both achieving these two things is actually very, very critical task. So this look, if you see, so what you do is when you try to increase the film thickness, so how your loss substantially, the optical overlap between the photonic and photonic mode starts to increase. But again, increasing thickness means and increasing cross section means you have a more on chip area, right? So these are some of the very good work where with this platform a better mode confinement compared to previous one have been achieved. So after the germanium on GOS platform and the graded silicon germanium waveguides are the next thing, and they actually proved very well for the multispectral. Now the things people started to design the detectors and sensors for those which were actually working for quite a larger bandwidth as compared to the earlier ones, right? But again, here the issue was the lattice absorption contribute to the waveguide propagation losses beyond 8 micrometer was the problem. And in fact, still the thrust for the longer wavelengths is still to be achieved, but it was a good step to go further in this field. Right. So if you see this example, germanium rich silicon germanium waveguide. So in this you could see that you have a very good confinement in TE mode, but in the TM mode, the mode is having the free carrier absorption in the substrate, right? So there is an absorption of the carriers into the substrate in the TM mode. So this was actually one of the very good paper. And then continuing this, a person was able to achieve different absorptions at different peaks by varying the doping. I mean the concentration of germanium and silicon germanium. While it varied from 0.1 to 0.9%. Then again, once again, SOREF come to rescue in 2006, back in 2003 earlier. I think I just end up, okay. So just repeated this task. But then continuing the SOREF work, the Cheng actually built the complete photonic integrated circuit on a chip, right from fiber to on-chip grating coupler. You see from fiber light has to come and then coupled to the grating coupler. Then you have the graphene or 2D material sheet on top of the waveguide platform. So where your sensing environment will be there. So this kind of platform can benefit most of your biophotonic sensors. The waveguide enables absorptions up to a range of 0.13 responsivity at 1.5 volt bias, and this worked well at room temperature. So things started to increase. So you see the feature size, 10 micrometer, and over here the sub-wavelength gratings have been used to couple the light from the environment or the verifier. So SWG quick review that these are the cladding functions. What that does is they mechanically support the waveguide. These are periodic structures. To synthesize a cladding core index contrast enables light guiding for fundamental mode, and to allow the flow of hydrofluoric acid, which is used as a solvent in the fabrication process of the VOX. So it really helps. So the photonic crystal, now we come to this point. These are nothing but their acoustic counterpart. Photonic crystals are known well for this thing. And when you combine these two things, you come up with this photonic platform, where you actually are going to engineer the band gaps of your photonics, where you want the light to prohibit, and the photonics where you want the sound to prohibit, right? So you create defects and you selectively allow the light to pass through certain paths on a chip. So in a very quick description of this. So during the past few years, there has been increase in interest in this field, especially because it is allowing you to have dual confinement of both photons and phonons on a chip, right? And in fact, recently it has also been shown that simultaneous gaps have been captured using homogeneous SiO2 slabs also with the periodic arrays. So let's say some of the very initial works. So the photonic crystal actually deals with your acoustic modulation of a confined photonic mode waveguide inside a cavity. So the optomechanical interactions have been widely studied for telecommunication applications for years, right? Literally for years. But since after 2009, people started working on this platform for sensing applications. And so our purpose is to emphasize this potential for photonic crystal to be an efficient tool for sensing at Midway Ir. So this was the very first work where the simultaneous band gap simulations were done for photonic platform in console. So it was just a line defect created, and a periodicity was given by the cylindrical rods to prohibit the phonons to leak out into the sideways. So what happens is, by creating the phononic band gap of some gigahertz, so you prevent the phonons to leak out into the substrate. So this is what you achieve the good transmission reflection of the your photonic and sonic band gap. So photonic band gap is due to a high elastic contrast, the photonic one, between air inclusion and the silicon matrix in relation with the scattering of the elastic waves. Then you see, due to the large contrast between the refractive indices of air and silicon, the transmission curves of the optical waves give rise to a series of pass bands and stop bands. And then finally you have the this photonic transmission, how your photons are made to are captured in between the cavity. Why? Because you have a photonic band gap created, and you change the size of these holes in the mid, and there actually your mode is confined within that, and it won't be leaking out in the boundaries. So this is the concept, and following this concept you have some more work, and people try to vary the geometry by doing this different dispersion engineering. So I'll quickly move this thing. So this is another example of a wisping gallery modes in a photonic cavity. And then you have silicon photonic crystal waveguide, right? This is a very highly cited paper, which actually elaborates your intra-mode and inter-mode forward scattering, brilliant scattering, forward in a forward mode. So a quick description. So the topology, if you see, just go to the bottom right, in the photonic engineering part, yes, by engineering both the photonic and phononic bands, we can actually achieve, a non-linear coupling gain up to 3 to the power 10 to the power or 10 to the power 6 order watt per meter intensity. That's a much higher non-linear gain, and we still want to have more and more non-linear gain, because achieving more and more non-linear gain would mean that you are able to prevent the thermal phonons from getting lost into the substrate. So we are saving the part of energy. So then you have these kind of recently platforms. People have tried to, instead giving trenching it from the clad from beneath, they try to etch it completely and provide the support with the buried oxide layer, and then use these sub wavelength structures over there. These sub wavelength structures, you see the horizontal strips, those are acting as a phononic band gap, right? So these, as well as they are providing you the stability for the mechanical strength in the fabrication process. to your normal waveguide. So general analysis of how your waveguide length will change the transmission through the waveguide. And this is again one of the proof of concept of the work. Another one, this one actually I refer to as my base work. And because here, you see in the mid, you have the complete ridge waveguide, and then it is supported by the phononic band gap provided by this plus geometry size. So plus is actually the single unit cell. So this unit cell is repeated in both x and y dimensions. So you go on to repeat the periodicity. What happens is, it becomes the photonic band gap becomes more stronger and stronger, and you might end up losing your actual photonic band gap. So you have to very carefully decide the number of periodic layers that you want to choose for a particular application. This is actually unit cell that I was talking about. The width and the height of this will vary as per the wavelengths. Correct. And this is actually what you get, the dispersion curve, the d omega by dk relation I was talking about. So the idea is of the photonic crystal is to slow down the wave, right? So you slow down because you are trapping the light within a cavity, and you're trapping the phonon energy also, right? So you are trying to trap the energy. So how you do it? You try to achieve the group velocity of both photon and phonon. You have to achieve the similar phase matching conditions between the two. Once you achieve the phase matching conditions between the photon and phononic momentum, you will be able to trap them inside the cavity. So this significantly enhances the optomechanical gains in both conventional nonlinear fibers as well as suspended silicon waveguides and hybrid silicon nitride waveguides. Let me just go on to shift. I think I'm running out of time. So this is another first of its kind photonic cooling in continuous medium of silicon waveguides, right? So this also presents both the Stokes and anti-Stokes detuning, and actually very compared to the previous works, very large detuning was attained, and with very good mechanical stability, this work was fabricated and actually experimentally tested. While prior works were most of them were theoretically talking about the exact simultaneous band gap measurement. And this again is based on the germanium photonic crystal waveguide. Earlier was a silicon based, and then people use the germanium based work. This is also simulated in COMSOL. And then the person analyzed the different kinds of thermal vibrating modes. The torsional mode, longitudinal modes, and flexural modes have been analyzed. So how you can prevent those modes from propagating into the boundaries. Okay, then another good materials are chalcogenides because they have very good anti-reflections capability. So preventing these things also will enhance your photonic coupling. So some of the very recent state-of-the-art works you could see as application point of view. This one is the electro-optic readout that you can form using this photonic platform, right? This is the same image of the double membrane sensor and zoomed in view on the center of the bridge where the photonic crystal cavity and the part of the photonic crystal waveguide are visible. Then another one is an all optical readout that we are actually trying to provide a substitute to the Moore law limitation, right? So this you see is a work by Liu and Tianren from 2020, very recent work. The compact integrated optical motion sensing at shortwave IR. The heart of this sensor is an optomechanical direction coupler that comprises of 4 evanescently coupled waveguides. So you see this one, the 2 top ones are fabricated using suspended platform. And now, continuing this, we actually presented a mathematical approach in the atomistic simulation model for photonic structure in a NIST-sponsored webinar series. So we just presented. So actually, most of the works I found was you have to calculate photonic and phononic bands using different set of software environments. So what we are working over is we are trying to give a simulated mathematical platform. Although there is one available in the open source community, but that too is very complex and limited to certain problems. So my literal vision is to come up with an integrated simulation platform for this. So what it actually requires is, it requires you to couple these optical mode and mechanical mode equations, right? The Navier-Stokes equation and the Maxwell equations, and the phase matching conditions between the propagation constant of the optical wave and the stiffness constant matrix of the acoustic wave. And then you actually try to minimize the 0-point fluctuation to achieve enhance the 0-point fluctuation to enhance the detuning and hence the optomechanical gain. So two types of ways you can do that. Let me see. Just sorry for that. Okay. So so it requires you to calculate these parameters. So actually what I've been trying to work on is I'm trying to back propagate using some deep learning approach to get the newer geometries, right? So some of the recent works in our group you can find is all optical photonic crystals logic kits. It is a review provided by the Jeevan Jyot, and then you have the work this review fiber Bragg grating sensors. This has published last year, and it has almost got 29 citations over it, and all the citations are the experimental works based upon this review. And then the one that I was talking about is emerging nanostructured thermal absorbing that enables cost-effective image sensing. It will be online very soon. And then some of the works in our groups you can go on to find. Also, I would like to take this opportunity to introduce you uh, to this clean room facility, which is set by headed by Professor Arun Kumar sir, and he's actually my chairman of my research committee, and as a part of a group is my supervisor Dr. Neena Gupta ma'am, and we are actually looking forward to fabricate our device over there. So you can always reach out to this group, and you can check out the website on our college page also. So finally, I would just like to thank my PhD supervisors and also my research committee, Dr. Arun Kumar Singh, Dr. Divya Dhawan, Dr. Vasundhara Singh, whom I had very strong discussions before actually formulating my problem objectives. And I then would like to thank my organization, Chandigarh University, that offered me the study leave to pursue my doctoral thesis at Punjab Engineering College. And the final vote of thanks to my parents, friends, and colleagues, and especially the Global Scientific Guild team to give me this opportunity to present before such a wide audience. So thank you. Any questions?
Hi, everyone. My name is Bing Yan from Bangor University. Today, my presentation topic is PCM super lens for direct laser nanofabrication and optical super resolution imaging in far field. Yeah. And my research in interest include a dielectric microlens synthesis, microsphere based super resolution imaging, and laser material processing, micro nano fabrication, and fiber optical tweezer. So currently I'm a postdoc in Bangor University in super lens group led by Dr. Zhengbo Wang. And Bangor University was established in 1884. It's located in the North Wales near Ireland. And Bangor is a very small city and surrounded by the mountain and the sea. And because of the pandemic, the overseas travel is very difficult at the moment. So the attraction around Bangor are very popular this year. And many of them are listed as top 10 attractions in the UK for this summer. So if the pandemic ended, so welcome to Bangor. My research are mainly based on the microsphere lens technology. So as many studies shown, the dielectric microsphere with diameter ranging from few microns to 100 microns have a very unique optical properties. The first effect, as known, photonic nanojet, has a focus size smaller than the diffraction limit. The super resolution focusing effect now is widely used in laser nanopatterning and nano imaging. And the second effect is Waveguide gallery mode, at which the energy is trapped and harvested inside the microsphere cavity. And this is employed, widely employed in the optical sensing and signal detection. And the third one is the directional antenna effect, which means the microsphere perform a very strong directivity and is very helpful for signal collection. And some application derived from its optical property include super resolution imaging, nanofabrication, and the signal enhancement. So in 2011, Dr. Wang, my supervisor, has demonstrated for the first time the silica microsphere can resolve a 50 nanometer feature under the white light condition. And this technique employs the micro size sphere as a lens to excite and collect the near field evanescent information and form a virtual image at a, and then it is subsequently captured by the conventional microscope. And this record was further improved by a synthesis TiO2 microsphere to 45 nanometer, and then it's improved to 20 nanometer by using a confocal microscope with microsphere. So besides, many researchers have achieved subdiffraction feature through the laser-induced particle lens technique. Here is an example of laser surface nanopatterning using the microsphere lens array. So a resolution of 80 nanometer has been achieved by continuous turning the incident angle. And a different pattern can be fabricated on the surface of a large area without a photo mask. And the microsphere also play an important role in the Raman signal enhancement, and due to its optical directional antenna effect and Waveguide gallery mode. From the inspiration of my supervisor's work, numerous studies has with respect to microsphere-based super resolution imaging has emerged. So the motivation of my research was also derived from this. And the main goal is to improve the technology in terms of its image performance, like resolution and clarity, and also the ease of use and the reliability in practical applications. So in the past years, we have improved the image resolution by proposed pupil mask design on the microsphere and hybrid microsphere superlens and the dielectric metamaterial TiO2 superlens. So far, the 45 nanometer image capability under the white light was achieved by the TiO2 lens. On the path of the ease of use, we have developed a cover slip-like microsphere lens and the superlensing objective lens. And we are the first group report a biological superlens provided by nature, which is a spider silk superlens. We also try to integrate our particle lens into a microfluidic device for cell and virus imaging, and the unibody PCM lens, which will be presented in detail in this presentation. So the vision is our research development will be commercialized, and so every microscope user will have our Bangor super lens in their daily microscope use. Also, the research has revealed the microsphere-based lens have a capability of super resolution imaging, but the image field of view is often very small, typically only a quarter of its diameter, which is a big challenge for practical use. There are some solutions to overcome this issue. One is the using a micro lens array, which employs a monolayer close-packed particle lens to generate multiple images at the same time. But this method results in inconsequence image. The blind area between the lens cannot be imaged. And also the inconsistence of this microsphere array may lead to the uniformity issue of each image quality. And the second method is more mature, which is using the tip-based scanning techniques. For example, attaching the microsphere on a fine glass micropipette or on the AFM tip. So by precisely scanning it, the large area super resolution was realized. However, this technique involves a very complicated and very pricey control system. Also, you need a very professional operation skill. So we aim to develop a low-cost, easy to implement, and also universal to any microscope system for large area super resolution imaging. To achieve this, we employ a new design where the microsphere lens is a compound part, consists of a plano convex lens and a microsphere lens. We call it PCM lens, and which can perform as an individual optical probe, and then is able to perfectly fit it onto the ordinary objective lens to form, as we call it, the unibody PCM objective lens. And it has same appearance and the simple operation as the ordinary microscope objective, but also provide a non-invasive real-time super resolution imaging capability. Then we install it onto in-house built image system, a very simple system. And in our experiment, the PCM objective lens was kept static, and the sample was moved by the underlying stage. A side view microscope was placed horizontally at the side for monitoring the gap between the microsphere and the sample to avoid damage and contaminate. So the PCM lens has a very advantage of excellent reliability and usability, and it is can generate sub-diffraction photonic nanogel. So to make a PCM lens, we need a barium titanium glass microsphere, and with size around 20 to 50 microsize. And also the plano convex lens with pre-coated PDMS thin layer to stick the microsphere. So under the inspection of the microscope, the microsphere is carefully attached at the center of the curved surface of the plano convex lens, and the second PDMS layer was spin coated to firmly encapsulate the microsphere. Microsphere imaging usually use near field image mode, which generally within wavelength scale or even in contact mode. But for sometimes it's invasive and may bring limitation in imaging the sensitive samples, for example, some biological sample. So the contactless process is very essential to avoid this damaging. In this experiment, we evaluate the image performance, including the magnification and the resolvability at a different working distance. So firstly, we use IC chip sample with periodic pattern. They are 400 nanometer squares with 200 nanometer intervals. So with an ordinary objective, which is 40 magnification and 0.6 NA, and it gives us a very blurry image, and the detail information was lost. Then we added a PCM lens onto the objective and kept all other image conditions same. So we evaluate 3 different PCM lens, which have 25, 38, 52 micron BTG microsphere. By changing the working distance, we investigate their magnification and the image quality. So as we can see, all PCM lens significantly improve the resolution, and the pattern on the IC clearly resolved. The comparison between the 3 different size microsphere reveals that PCM lens with smaller microspheres shows greater magnification and at the same working distance. And in all size PCM lens, the magnification increase along with the increase of the working distance. And however, we also noticed when the sample is very close to the PCM, the image distortion appear obviously with the lens moving away from the objects. The uneven imaging performance and the distortion is gradually suppressed. But the contrast of the field of view reduced correspondingly. Therefore, there's a compromise between image quality and magnification, and it's necessary to make a trade-off to get the most balanced performance. In addition, smaller sample were used to further investigate the super resolution ability of the PCM objective lens. Here we use 38 micron microsphere PCM lens to capture a Blu-ray disc with feature of 200 nanometer stripes and then 100 nanometer grooves. We found that the oblique illumination and the partial illumination can help enhance the image quality. According to the previous slide, we know that image performance is better at the working distance with some range around 1 to 3 micron. So at a smaller working distance, the image quality was affected by the deviation of this illumination and between the center and the outer region. So at the working distance around 3 micron, the image exposed become more equalized. So the feature of the Blu-ray disc can be clearly distinguished with the magnification around 8. So after 4 micron working distance, the resolution is reduced and the super resolution is no longer possible. So to expand the viewable area, the scanning imaging is necessary. So in our unibody PCM objective, the lens is synchronized with the objective, and during the scanning operation, it is beneficial to keep the position of both objective and PCM lens constant in one position, and then in this work, the scanning image was performed on IC chip and the Blu-ray disc to demonstrate the feasibility of scanning imaging. Here, we also used the 38 micron PCM lens, and then its working distance was kept constantly at around 3 micron. So the sample was moved in XY plane, and by the motorized stage, the camera captured one frame when the stage move a step, and the scanning path is line by line scanning, as the yellow dashed line show. So in the end, there are 100 frames were recorded, and then a large area image was achieved by stitching those 100 images together. And here's the video showing the real-time scanning of PCM lens. So it's very fast and fast process, and the resolution is hugely improved. So in the experiments, we found that the encapsulation data by the PDMS around the microsphere is can be slightly varied due to some microsphere size signals of the encapsulation layer PDMS, and also the process deviation. So to further investigate whether this deviation will affect image performance, so we to understand the focusing property of the PCM lens in different capped case. So computation modeling was performed. Here's the comparison was between the different encapsulation condition from 0% to 100%. So at the 0 encapsulation, the microsphere generates a hotspot at the boundary of the lens, which cannot be used for image because it doesn't generate a virtual imaging. And apart from that, all other cases can focus light into the elongate shape at around 7 micron away from the microsphere. And the light intensity is hugely enhanced by 3,000 times. So we also found that the difference in encapsulation in the range between 20 to 90%, they have a negligible effect on their focal length. So which means the microsphere performance doesn't affect by some process deviation and also the thickness of this PDMS layer. And the simulation also is consistent with these experiments, which means the imaging performance is affected by the working distance, and the super resolution phenomenon always happen within 4 micron working distance. In addition to the super resolution imaging, the PCM lens also can be used in nanopatterning. Here's a setup. It's slightly different from the imaging system. The PCM lens was simply bounded onto a 3D printed holder to build a detachable lens module. And along working distance, zoom lens was placed horizontally at the side to monitor the gap between the microsphere tip and sample. And we use a femtosecond laser with 800 nanometer wavelength, and project the laser onto the PCM lens. And the scanning was performed by using a piezo stage. So in this experiment, there's no objective lens was used. So the sub-diffraction focusing is totally determined by the PCM lens. The focusing performance is systematically investigated by the optical simulation, also the experiment. The simulation results shows that the PCM lens with 50 microsphere can generate the enhancement on the electric field about 2,000 times. And the calculated focus spot size start from 200 nanometer at the boundary of the microsphere, and then gradually rise to about 700 at a distance increase to 11 micron. After that, it reached to microscale size due to the light divergence. The super resolution, which is about half of the wavelength, is found for working distance within the 6 micron. The focusing performance is also verified by the experiments. So as can be seen from this figure D, and the working distance increased, and the patterning size is consistently increased. So with the working distance at 2 micron, we can achieve the feature size down to 230 nanometer, which is lambda by 3.48. So in the scanning patterning mode, a laser was synchronized with the piezo stage and by our in-house developed controlling code. So which control the laser beam on and off while the sample is moving. Here we present the 2 scanning mode. The first one is the point by point, and the second is a continuous mode. In the point by point mode, the laser emits a pulse when the nano stage complete a step. So therefore, it forms the dot outline of the shape. And then on the other hand, the continuous process can give us a continuous line. In the continuous line mode, the line size is we can achieve is about 300 to 350 nanometer. Furthermore, it's important to note that the process system is not limited to fabricate a simple line on the dot pattern, but also flexible enough to write a different, very complicated patterns. So here, the right figure shows the arbitrary pattern on the silicon and also the metal and glass substrate. So the most recently, we have successful combined the imaging and the patterning function into a single system to create potential revolutionary laser nano manufacturing instrument to couple with the simultaneous super resolution imaging function. And this one can meet the challenge in laser nano production and optical imaging. So here's the demo of the imaging during the laser process by our developed PCM lens. So here's the conclusion. So the unibody PCM lens can simplify the laser marking and the super resolution imaging process, and the patterning and the image resolution are experimentally and theoretically tested. And the best image resolution in here we demonstrate is 100 nanometer, and the best patterning resolution is 230. The PSM lens is very versatile and can turn a normal microscope into a super resolution image and laser marking system. And the above work was published last year in Optical Letter and Applied Optics. Okay, thank you very much.
I'm going to talk today about our attempts towards integrated atomophotonic circuits. Our team consists of two groups. The first one is myself and Folly Ayova. We are atomic physicists from NPL. And then Andrew Greer, Nikolai Gadegard, and Anthony Kelly from the Photonics group at the University of Glasgow. Therefore, it will be some atomic physics in my presentation, but I will try to keep it simple. There is a content of the talk. First, introduction, which includes atomophotonics and Bose-Einstein condensation. Then I will explain about atomophotonic circuits concept and its elements. We'll talk about quantum inertial sensors based on such circuits. We will describe briefly our vision of the design of all optical atom chips. We'll show the current status of manufacturing of suspended waveguides for such circuits, and we'll briefly discuss applications. Atomophotonics is a new science, and also which is about guiding circuits for ultra-cold atoms. And there are mainly two types of waveguides which are used for atoms. These are magnetic waveguides or optical waveguides. And magnetic waveguides are based on current carrying wires which are integrated into the silicon chip. And you probably know it as atom chips. And the principle is based on generation of non-uniform magnetic fields by that currents near the surface of the chip, and in presence of additional offset and bias fields, you can form a magnetic potential for atoms which is lying so above the wire at the distance of about 100 micrometers. And the optical circuits can be formed by different ways, and one of them is called painted potentials. It is when you have a sharply focused laser beam and you move it fast along a certain pattern, and the atoms will see the time average potential, and therefore they can propagate along such a painted waveguides. You can draw also a circuit, so the right picture shows basically the atoms in such a circular resonator in the ring waveguide. What I want to mention also, the problem of these both types of waveguides and circuits for atoms is that it is not clear how to create a coherent beam splitter for atoms, which is a key part of any interferometer. So, in any optical interferometer, also you need, to use splitters. It is either, so semi-transparent mirrors or polarization elements or diffraction gratings. The same is for atoms. So we need a splitter. Yes, and people are thinking also even about integrating, so such magnetic waveguides, atomic sources of ultra-cold atoms and the detection systems in single atom chip. So people are working on it. The BC, the Bose-Einstein condensation, was theoretically basically developed by Einstein and Bose around 1924. First was demonstrated for liquid helium. And then in 1990s, in several groups, it was also demonstrated for dilute atomic gases in magnetic, or in that time in magnetic traps. And these three people, Cornell, Ketterle, and Wieman, got the Nobel Prize for that in 2001. The effect is quite simple. If you have an ensemble of bosons in a trap, or in given case is a box, at some critical temperature, when distance between the particles become comparable to the de Broglie wavelengths, atoms start to be condensed in the ground energy system, ground energy state of the system, and that is a BEC, and it is described by the same wave function with the same phase for all atoms. So therefore they're undistinguishable, and this is the microscopic coherent state of atoms in this case. What is important for us in our applications, the BEC has quite high density of atoms, usually 10 to the 13, 10 to the 14 atoms per cubic centimeter, and quite low temperature. So typically the critical temperature is about 100 nanokelvins. And this is important because we are going to populate with atoms tiny structures. Therefore, you need a high density of atoms. Also, we don't need for our applications the coherence of these atoms. These atoms still can be thermal. Based on BEC, you can build an atom laser. So basically what you have at the top, these spots are atoms which are either fully condensed at the right or still also in thermal state. And if you make in that trap a hole through which you can gradually release some atoms in the field of gravity, you see that, so in the case of BEC, you can produce quite nice coherent beam, which is similar to laser beam. And at the left, it is a thermal one. Okay, so why I mentioned that? So basically from invention of lasers and their development led finally to development of photonics. In the same way, invention of atomic Bose-Einstein condensate is leading now to development of atomtronics. And actually, our proposal basically combine all these 4 different technologies, and these are atomophotonic circuits, which can have applications in quantum sensing and quantum computing. The whole idea is based on my 30 years old idea about 2-color evanescent wave dipole trap for atoms. So a total internal reflection you is producing in vacuum evanescent light field, which has no propagation depths around wavelengths. And in our case, we use 2 such waves of different color. One of that is red detuned with respect to the main atomic transition, and another one is blue detuned. Therefore, the signs of the forces in these 2 fields are opposite. So blue field repels the atoms, and red one attracts atoms to the highest intensity region of this wave. Therefore, if we, in addition, will produce different penetration depths for these 2 waves, which can be adjusted by the angle of the total reflection. And you can organize such a case that blue repulsive field is short range and red field attractive is a long range force. And therefore, it is formed such a potential that has a minimum at certain distance from the dielectric surface where you can trap your atoms. It is very similar to bonding of atoms in the molecule when you have short range repulsive and long range attractive force. Some people called later on this push me, pull you principle. Okay, and at the bottom you see if you sum up the two optical dipole potentials in the evanescent light waves of different also penetration depths, you can have as a result such a minimum at certain distance from the surface. Now, this principle can be used also for waveguides. If you populate your waveguide with red detuned and blue detuned light, you can trap atoms and guide them basically along your waveguide. Therefore, such waveguide at the same time is guiding photons and atoms. That is why I decided to call it Atomophotonic waveguide, basically to reflect its property in full. Another advantage that this Atomophotonic waveguides can be bent, and this is a useful property which makes it possible, to create new types of atom interferometers, which is not possible in free space, but I will describe it later. We found that the best choice of the waveguide is a suspended waveguide for our applications, because in that case, so from both sides of the waveguide is an air or vacuum in our case. And this provides the largest penetration depth of the waves in vacuum, which makes it possible also to keep atoms further away from the surface, which I explained that it is important. And yeah, and for us important to have both modes, the blue detuned and red detuned, are single modes of that waveguide. And we calculate and found also the parameters, the geometry of that waveguide when both of them are single mode, and it is shown on these graphs. So for our case, we are using 720 nanometers and 850 nanometers, just because the main transition of rubidium atoms is at 780 nanometers. So one is red detuned, one is blue detuned. We calculated also the atomic potential, optical dipole potential for atoms. So we included red detuned field, blue detuned field, and the van der Waals potential, so which is attraction of atoms, also towards the dielectric surface. You see the green curve here, the combined potential of blue and red light in evanescent light fields. And when you add up van der Waals, the minimum is shifting towards the surface and become a bit deeper, but it is still possible to hold atoms in such a potential in spite of presence of van der Waals attraction. And here's calculated potential. You see its minimum is located at the distance about 400 nanometers from the surface. And the width of this strap, which is slightly bent, is about 2 micrometers, which is the width of our rib in this case. We found for our applications, so we need that high intensities, which correspond to powers about several milliwatts in each of the modes. And what is important that, so these potentials for atoms can contain only one or two bound states, which means with narrow waveguides, we can realize single mode atom waveguides, which is important for interferometry, and it is impossible to realize it in free space and also for focused laser beams because they're much too wide. Another important element of such circuits would be the waveguide break beam splitter for atoms. And the idea how to make it, so if you have two crossed laser beams or guided evanescent wave fields, of the same frequency. In the cross region, they produce an optical lattice. That is just interference grating produced by interference of the two beams. And this optical lattice can be used as diffraction grating for atoms, basically to split them between the two arms of the cross. Experimentally, we demonstrated that first with focused laser beam, focused down to waist about 15 micrometers, which was far detuned from the atomic transition to the red side. And it is published in scientific reports in 2017. I will show you some results from there. So we have two waveguides cross at right angle. And the cross region here is a dark spot in that line. That line are atoms guided by that laser beam. And we can change the amplitude of the optical lattice in the central region by changing the mutual polarizations of the beams. We can have no lattice, small lattice, and deeper lattice. And depending on the depth of the lattice, we change the fraction of atoms reflected in the second waveguide. I'm going to show you some videos. I hope I will be able to do that. Yep. What is shown here? So first, we have BEC loaded in one of the waveguides, then it is accelerated towards the cross region. And here is no optical lattice. You excite some transverse modes after the cross between the beams, because so it perturbs the motion of atoms. And this shows this zigzag motion after shows the multimode behavior of this atomic waveguide. If we increase slightly optical lattice, we see splitting to the second arm. If we increase it further, most of the atoms are reflected. So it is working, but in optical waveguides, it would be easier because you need to perform such a precision alignment of the laser beams, and here also the beams are much narrower. That is the size of the rib, which is in given case about 3 micrometers, and this is calculated, so optical lattice at 720 nanometers. Now about measurements of inertial forces, in given case acceleration with interferometers. The idea is simple, to measure acceleration, you just measure displacement of the atom after, certain propagation time, t capital. And from this, you can calculate the acceleration. With interferometers, all the trick that you split with diffractional grating, first atoms in two different parts with different momentum, then you recombine and you produce interference fringes in the detection region. And when you have the fringes, you can more precisely determine the displacement of atoms because you measure just the position of the central fringe. And if you add the third grating, and this makes so a full Mach Sender interferometer, you compare position of the grating with respect to the optical grating, which is producing the splitting. And as a result of that, you don't need to measure position of the fringes. You measure just population in the two output ports with different momentum. And this gives you information about your displacement. In practice, for free-falling atoms, in this case, in the fountain configuration, you apply 3 light pulses, you split and recombine atoms. And the problem here that in gravity, this is example of gravimeter, if your time is 1 second, then the height of the trajectory is already 5 meters. So it becomes first difficult to build such a system and difficult to use. Therefore, in practice, they use much smaller interrogation times. For waveguide interferometers, you don't have that limitations because your atoms can be quite slow, can have velocity of 1 centimeter per second, can be guided. And if your gravity is perpendicular to the plane of the interferometer, so the guiding potentials support atoms against falling in the gravity, and therefore you don't feel it. But you can still measure accurately the small acceleration in horizontal plane. By the way, you see here, so these are two beam splitters in the cross regions, which are used first to split atoms between the two arms, and second time to recombine and produce output. And you see that for length of this interferometer, for just 1 centimeter velocity, 1 centimeter per second, total flux of atoms 10 to the 5 per second, it can have a sensitivity up to 10 to minus 10 meters per second squared per square root of hertz, which is quite high and quite good for such a small device. You can build different configurations of such interferometers. This is a classical Michelson waveguide interferometer where you have just single beam splitters, 2 arms, and then you have additional mirrors for atoms formed by blue detuned potentials. So atoms first split and then return back and diffract another time at the lattice. So it is very similar to optical Michelson interferometer with a single beam splitter and 2 mirrors. And you see it can be also quite sensitive to acceleration. It is possible to show that we can even measure the gravity with Mach-Sender interferometer, which is deformed like it is shown here. The problem that to measure the gravity, you need to take into account that so it is very high acceleration and atoms will be accelerated to velocities much larger than their initial velocity. And therefore we have shown also that the length of the 2 arms should be different. The first one is horizontal, where you don't feel the gravity at all, and your atoms moving with constant velocity. But in the U-shaped arm, atoms first accelerated to high velocity, then decelerated and arrived to the second splitter with the same velocity. But to provide the same propagation time for both arms, you need to satisfy the next condition at the left. And for quite small size of it, so the width of 1 millimeter and height of 1 centimeter, sensitivity to the gravity can be 0.5 microgal per square root of hertz, while miniature devices based on MEMS are worse by 3 orders of magnitude. So they usually measure about 1 milligal, and this is the best. Okay, how about the design of the atom chip? So it can be organized something like that. So first you need to produce the BEC, and usually you produce it in free space above the surface of the chip. Then you need to provide transfer of these atoms towards the surface. This can be done with a moving optical lattice. And after that, you need to accelerate atoms along one of the waveguides, basically. So at this stage, you produce atoms in some, surface atomic source, which emits atoms into the waveguide. Then you split, propagate, diffract second time, and then you need to detect the relative number of atoms in the 2 output ports, and also to make it working. Okay, how to produce suspended waveguides? We have chosen in our approach silicon dioxide suspended waveguide because it can have very small losses, and it has good transmission in near infrared and invisible range. And fortunately, also it was already work, also published in 2012 by a Chinese group in Optics Express, where they demonstrated that it is possible to produce such a waveguide. In their case, it's for 1.5 micrometer light, certainly for different applications. but they demonstrated, so different shapes of such waveguides and quite low losses. Actually, propagation losses were measured as 0.4 dB per centimeter, which is quite good. And they also demonstrated, so that they can be bent. And this graph shows, so basically the losses at bending by 90 degrees. So we simply tried, to reproduce, so these waveguides at Glasgow, and definitely for our slightly different, so parameters of the waveguide, because now we need to guide in two different colors at the same time in the same waveguide, and they should be ground modes. And the way of production was quite standard. We used combination of dry and wet etching, so to etch silicon, so base under the suspended waveguide, and it is working. Yeah, so here, so on the right, it is shown, so the diaphragm produced by such a etching. And the next stage, we changed just square openings to round, because we think it will provide, better mechanical stability to the system. And in addition, we were able to etch such trenches from both sides, because we will need it for optical coupling of light. And it was tested also the producing of the rib, so, and all is working. So therefore we hope soon we will have, such structures. Okay, certainly such miniature sensors will be quite useful, also for many things, taking into account the high sensitivity. First is inertial navigation, where you need to use accelerometers and gyroscopes, which is useful when you don't have access to GNSS. Climate change monitoring can be done with sensitive gravimeters and gravity gradiometers. So, for example, you can measure the ice caps, so, and the changes. It can be useful for metrology, for cable balance, optical at atomic frequency standards. So while you're measuring the gravity, its absolute value. Can be used, the arrays of such surface dipole traps can be used for quantum memory, and we are working on the theory of it now. Potentially, it can be useful for quantum computing, some quantum logic elements. And here, yeah, so the pictures below shows different applications of gravimeters mainly. Yeah, so it is geological gravity survey, also exploration of minerals, oil, gas, and underground water, and also for civil engineering, because so before you build something, you need to investigate it, what is under the ground, are there any cavities, pipes, and so on and so forth. Okay, our next steps, our plans, basically, first certainly to manufacture the first suspended waveguide, to test it with two color coupled light of right intensities, so in air first, then in vacuum, because these are two different, thermal regimes. Then integrate it in the existing system with rubidium Bose-Einstein condensate, and to demonstrate guiding of atoms in such a structure, which will be first step to realization of this new technology. Thank you for your attention.
So
So the optical equivalent for operators with weighted density matrix and spectral component on compact supports is defined for the projector operator. The definition of the first approximation correction orders is demonstrated to depend on the definition of the parameters qualifying the definition of the weighting support control function. The investigation is apt for system constituted of intense non-monochromatic laser fields. The power spectrum of the operators is this way decomposed as a sequence obtained after the majorizations of the operators after those of the weighting function. The power spectrum is not needed to be expressed as a sequence of majorizations, where such majorizations do not apply to pure states. The control of the spectral analysis can be achieved in order to distinguish among several contributions, and the calculations are performed for the most extreme case of the long time limit of the error estimations and for other applications. So in summary, can you see my pointer? Can you hear me?
Yes, we see your pointer.
And you can hear me?
Yes, yes.
Thank you. So I will revise the parts of the demonstrations of the optical equivalence theorem, which will be needed for the new developments, and then the new developments of the theorem will lead to new definitions for operators, density matrix, and states. Then applications will be proposed and listed. So just to introduce the structure of the topic, new extensions and developments of the optical equivalence theorems will be presenting for the implementation to establish a relation between the sequences of the density matrix operators functions and their expectation values. The approximations necessary for the applications to the new systems will be calculated, and the evaluation for the approximations of the weighting functions necessary for the expansion of the density matrix will be performed. It will be performed at the request approximation order. So the optical equivalence theorem demonstrates the connection between the classical probability distribution formalism and the density matrix for a quantum mechanical system. And here there are some references on which the demonstration is based. And it is based on the comparison of the expectation values of the mean of the measurements of the operator measurements in the Hilbert space and in the phase space formulation. And in particular, the demonstration that I will follow is not based on any hypothesis on the Fock space. So among several demonstrations, this one is not based on the number operator and allows one to construct a diagonal density operators for coherent states. It's possible to apply it also to other degrees of freedoms where the integration can be extended on the entire Fock occupation space, where annihilation operators and creation operators can be defined. The interest in this demonstration relies on the particular hypothesis assumed for the states of the system. For unbounded observables, a function can be set to be replaced with a suitable function, where S is a suitable support controlling function for phi in the definition of phi through appropriate parameters, which we will see in the applications, how to specify them. And the weighting, it is possible to define a change of variable in order to obtain a weighting support, a weighting function of compact support, which can be further defined acting on the states on the functions phi, and in order to define the density matrix. Phi, the found phi is on compact support such that the corresponding density operator is finally diagonal after the change of variable. This definition of the density operator is well defined, and it's an approximation of sequence for unbounded operators for the definition of a density operator, which is on the contrary directly defined for bounded operators. The new applications for the new states with an almost infinite expectation values operators can be applied in the cases such as, but not necessarily only, of interactions of extremely intense laser field background, highly energetic quantum processes, and semi-classical ones, infinite momentum classical states for which the high energetic process is the correct phenomenological experimental approximation, in the sense that it exhibits the same high energy limits. The partition function for the semi-classical description for the quantum optics description and for the optical system description for given n the occupation number sequence can be calculated. In all the approximation here described, the weighting support function is demonstrated to satisfy by definition the following property. That is, that it admits the following majorization for unbounded observables. And the definitions of these approximations are to be developed between the framework of infinite valued operators eigenstates for extremely high energetic processes. Then just to point out the main steps of the developments, we see that the weighting support functions has the property to straightforwardly be extended to the convergence properties in the trace class norm, as well as to the definition for orthonormal basis for unbounded observables by transitivity, where suitable high order corrections can be evaluated. And operators can be defined with weighted density matrix and spectral components on compact support, and the following majorization holds. And the two majorizations are obtained for the projection operators. The definition of the first approximation correction orders is therefore very important, depending on the definitions of the parameters beta and lambda in the definition of the weighting support Poltron function. Which is defined for unbounded operators and which is to be applied for almost infinite valued operator eigenstates. Operators A admit a weighted density matrix and spectral components. It is possible to apply the results for the expressions of sequences of observables of unbounded operators, such as the density matrix, to the calculations of the other operators for quantum mechanical systems to be compared with the corresponding optical systems. The definition of the first approximation correction orders has a specifying functional dependence on the definitions of the parameters respectively. The related results are obtained by considering the properties of quantization on null hypersurface quantization techniques. The investigation is consistent for systems constituted of intense non-monochromatic laser fields, and the power spectrum of the operators can be decomposed. It is not needed to be expressed as a sequence of majorizations for the density operators for a finite momentum, which involves the Fox representation. The observables for the interaction processes can be schematized within the approximations of the expectation values of the density matrix corresponding to the infinite energy momentum laser fields as the corresponding eigenstates. Then there are some remarks which are in order, for which compare with the original demonstration, with the demonstration of the first part of the theorem. The remarks are about pure states in the momentum representation by means of the density operators with a suitable projector. And the weight function allows to classify coherent states and incoherent states in a radiation background field. Coherent states are represented by a finite number of creation operators with as coefficients arbitrary complex number. The weight functions are tempered distributions which are integrated on real elements of area. In particular, it is found that it is a linear combination of two-dimensional functions of a finite number of its derivatives. Within the definitions obtained, density operators in the momentum representations are weighted functionals defined, and quasi-probability distributions are expectation values for the corresponding density operators. Integral representation for the density operators can be found, and for incoherent states, the density matrix can be rewritten as a limiting procedure as a sum of neighboring states, where this property still holds in the new developments. The corresponding weight functions are tempered distributions only for two states. These mismatches are solved by our representations of the density operators, which we have found in the case of almost infinite laser background field independent of the Fock representations, and discrepancy for quantum states in the power spectrum as expressed for optical systems by the correction terms, which contain of the found weighting functions at all non-equal trivial weights characterizing the Fock spaces. The corresponding Fourier decomposition holds. It is possible to look for applications. For the first application I have could appreciate is the long time limit for the error estimations, and for which in the case in which the quantum correlations of multispatial modes can be examined by means of the experimental errors due to the experimental noise, and also due to the attenuations of the experimental apparatus for which the optimization methods can be described. So within the control paradigms for fundamental tests of quantum mechanics, the long-time limit of the error estimation can be taken into account and can be formulated theoretically as it has been done in the references given. With an evaluated power spectrum where the quantities are defined. And for the quantum, for the analysis of the quantum correlation, it is possible to calculate exactly the long time limit for the error, where there is a correction term, which consists of a non-trivial summand plus the corrections to the other parameters, which were the parameters which were characterizing the object found in the new developments of the theorem. Further, the Fourier decomposition for the modes in this case holds, and it is approximated by one containing particles with infinite momentum on Minkowski space-time. The peculiarities of intense laser fields containing particles with very large values of the momentum and not an infinite momentum can be ascribed to the properties of semi-classical optical systems, for which the dimensions of the system are larger than the Planck length, but whose constituents are of a quantum nature. Then further applications can be found in the case of cold atomic ensembles and cold atomic traps, jump processes between states. quantum correlations of multispatial modes for Gauss-Markov models, and uncertainties estimations in quantum metrology. Thank you for your attention.
Hello everybody, in this presentation I want to talk about the photonic crystal umbrella for thermal desalination simulation studies. By me, Hassan Syed, Assistant Lecturer at Physics Department, Microsphere University. Under supervision of Professor Dr. Araf Hussein Ali, Department of Physics, Microsphere University, Egypt, and Professor Dr. Thomas Krauss, Department of Physics, University of York, UK. The outlines of my talk, I will be talking about the introduction of the water crisis around the world and the suggested solution for it. Then I will be talking about in chapter 2, photonic crystal, which is the first paper for me, the style photonic band gap material for water distillation. Then, in chapter 3, we will be talking about time resonance salinity sensors. And chapter 4, photonic umbrella for thermal desalination. And finally, conclusion and future work. Firstly, the water resources around the world is divided into two parts, 7% fresh water percent only. That 3% fresh water is a source of all over the world, and it's divided into 4 main parts, as we show in the figure. Also, surface water is divided into 3 parts, rivers, swamps, and lakes. The water crisis around the world, as we show in the photos, all over the world must be devoted the energy, the water crisis around the world. If we show, if we look about the map of the world, we have about 19% high extremely stress. And if we look at Egypt of yellow color is low to medium stress. So we must be searching for another renewable source of water to solve this water crisis in Egypt. So we can see that save water equals save life. Solution of freshwater crisis in water in Egypt. In Egypt, we have immediately and very important crisis, which is the Nahda Dam in Ethiopia. And the solution of this is we have another source of water in Egypt from the Congo River. And this river requirement 600 kilometer length to transfer water from Congo River to Nile River. And this needs forestation to overcome the high difference to cost for 9 billion USD. As Nile River doesn't have the capacity for an excess for this huge amount of water, and we must be drilling a new river in Egypt and Sudan is costed about 15 billion USD. So the desalination is a promising solution for this water crisis in Egypt. The desalination is a process of removing the salt and mineral from saline water to produce fresh water, as we show here. So desalination is a promising solution to water crisis. As we say, that desalination is the process of removing salt and minerals from saline water to reduce fresh water. The desalination technique, we have three main types of desalination: filtration, evaporation, condensation, and crystallization. So the main three types of desalination techniques is RO, MEE, MSF. So we have a small comparison between these three types of desalination. The comparison will be dependent on the cost of each process and the power consumption. So if we look about the cost, we have the reverse osmosis is the lower cost from the two other systems, and the power consumption. So to produce optimum desalination mechanism, we must be connected between cost and energy consumption. So desalination is the process of removing salt and minerals from saline water to reduce this water, and it is normally considered that salinity below 500 ppm is suitable as a drinking water. And in this picture, we have the second big station in the world, in the California, USA. Desalination is an expensive energy hub, but improvements are on the way. Improvements to save the energy for producing the fresh water, we must be dependent on solar desalination. The solar desalination is used electromagnetic waves to heat the saline water to evaporate, and then the condensation to produce fresh water, as we see in this figure. Here, this black material is good absorber and good emitter. Good absorber for electromagnetic waves from the sun, and good emitter to thermal energy to the surface of the water. And this material must be two-dimensional photonic crystal, because this material or the holes inside the material allow the vapor to flow up and then condensation to reduce the fresh water. The photonic crystal is an artificial material in periodicity 1 or 2 and 3 dimensional, as we see in the figure. As a type of photonic crystal, we have two main types. Photonic crystal in nature, like this photo, and artificial photonic crystal, which we concerned on our project. Application of photonic crystal. Photonic crystal used in many applications, such as solar cell. In solar cell, it used in anti-reflection coating and back reflector to neutralization the energy on the active area of the cell, and waveguides, and biosensor, photonic crystal fiber, and also the desalination mechanism, or exactly thermal desalination. This paper is restyle photonic band gap material for water desalination by me and Dr. Araf Hassin Ali, Dr. Thomas Strauss. In this paper, we will be talking about the considered structure, optimization methods, results, and discussion and conclusion. Firstly, we must compare between these three surfaces, the flat surface and porous surface and pyramid shape. As from the optical properties of these three types of aluminum sample, we have the absorption of the pyramid is increased or is greater than the flat and porous sample of aluminum. Here, absorption of the structure is depends on the morphology of the surface as we show in the figure. Simulation process and boundary condition. Our structure here is two-dimensional conic crystal. Here is air region. Is the air region. Wait, please. This is the air region. Then is the structure which absorbs the electromagnetic wave. And here we take one unit cell and the missing size of our simulation by complement physics. The boundary condition, we have frequent periodicity in the four sides of the structure. Here, the two sides and the other two sides. And part one is the direction of incident electromagnetic wave, and part two is the direction of the transmitted electromagnetic wave. Here is the downside of the structure. The pyramid's porous. If the electromagnetic wave or photon incident on the pyramid structure, it will be divided into two parts. The transmitted photon with red color and reflected photon with green color. And this green color is also divided into two parts, transmitted and reflected. So we can say that white incident on pyramid structure will have at least two chains of transmission into the material. But in our application, we need to store that material also. So coupling between the pyramid structure and the porous structure. The pyramid porous structure here in figure allow the vapor to flow up from this pore of the Photonic crystal. And this structure is flow up on the surface and then flow up through the pores inside the structure. And the different shapes of the missing size of our structure and the missing size in the functional multiphysics simulation must be 10 times smaller than the lowest wavelength of the incident electromagnetic wave. The parameters of the structure is pyramid porous. The pyramid porous air has many parameters, like the weight of the pyramid, the height of the pyramid, the radius of the pore, and the thickness of the material also. So, if we compare between these two structures, these two different structures of pyramid, porous, and pyramid, and flat and porous, with respect to its absorption in the visible spectrum, we have the pyramid porous structure is greater than the other types of Photonic spectrum. The special relation of aluminum and titanium. In our simulation, we use the optical parameters like refractive index and potential coefficient for the used material as a special relation which depends on the incident wavelength. If we look at this structure, by using porous pyramids, absorption seems very low, so we need to enhance this absorption. So we must adding or coated the material by dielectric layers. Because this dielectric layer is reduced. Because this dielectric layer is reduced, the dielectric contrast between the air and surface layers and this allow most instant photon to transmit it and absorb it inside the material. And here's absorption with different material, aluminum IN, and here is absorption of aluminum IN, aluminum coated by aluminum dioxide, and CIN coated by titanium dioxide. The effect of height and effect of area. The effect of height of the pyramid, if the height of the pyramid is increased, the absorption increase as we show in this picture, and then also by increase the radius of the pore, it allows more than photon to localize into the structure. And here we have a very important example. The structure has porous, but we don't have any transmitted photon because the radius of the pore is comparable with the instant electromagnetic wave. So the instant electromagnetic wave is will be absorbed inside this pore. And the morphology of the surface. In this structure, we have one pyramid in each unit cell. So each one pyramid has four pores in each corner. So if we replace this one pyramid with by four pyramids in each unit cell as in this figure. So by using four pyramids each unit cell, we have the absorption is enhanced by a remarkable relation as we show in this figure. So the conclusion of this paper, if we compare between the published paper on the absorption electromagnetic wave and our structure, we have water and aluminum cell and carbon nanotube powder, carbon nanotube cell, porous aluminum and pyramid porous CIN. Here is the phase absorption from the last literature survey of the structure. This is the first part of my presentation. The next part is picturing and photos one-dimensional time resonance for salinity sensors by me and Dr. Arafat. The outline is of consideration and modeling results and discussion, and the results and discussion divides into two parts: one-dimensional solid crystal and time resonance, and finally conclude. The motivation. We have the one-dimensional solid crystal is a periodic structure in one dimensional, and the two other direction is the material is homogeneous. And the time resonance is the interface between the metallic layer and periodic structure of one dimensional. So we are coupling between one dimensional crystal and time resonance to produce the salinity sensor. The salinity sensor consists of one-dimensional crystal and layers of saline water or any analyte, and this is the metallic layer on the substrate of silicon dioxide. The modeling and simulation. One-dimensional sonic crystals have different shapes. So we picturing the surface and so the surface. The picture in the surface here, each layer of solid crystal has shape of pyramid. And the total, each layer of solid crystal has total shape as we show in this figure. So, if we concern it on the sensitivity of the structure, we will be concerned on the important parameters of sensitivity and quality factor and figure of merit. One-dimensional sonic crystal. Here we have the one-dimensional crystal with different in periods, and here is the photonic band gas in this figure. So if we added a detect layer adding water, by adding a detect layer, it creates detect peak in the photonic band gas here. So by changing the index of studying water, we have differentiate between them as index. And by calculating sensitivity and light factor and sensitivity, we found that the sensitivity is very low. So we go to the naked part of the picturing surface. The picturing surface also gave me a photonic band gap, and also adding detect layer of saline water give me a detect peak, and it will be differentiate between different refractive index of water. And by calculating the sensitivity and quality factor and sugar of merit is still very low. So the last part is total one-dimensional. Total, by adding a fixed layer, we will be differentiate between different refractive index of saline water. And here is the color change. The localization of electromagnetic waves is the top of the total of each layer, as you see through here. And the sensitivity is low. The next part of this paper is the time resonance photonic crystal. This is the photonic band gap of one-dimensional photonic crystal from aluminum dioxide and titanium dioxide with this thickness. Number of periods. By changing the number of periods, we have more than one fixed beat on the photonic band gas, and we will calculate the sensitivity in this different types, or different cases, and analyze thickness also by changing the thickness of the layer from 100 nanometers, or sorry, 1000, 2000, 3000, and 4000 nanometers. Also, for picturing the surface of each layer with the gap, give me different number of sensitivity. So, conclusion of this part, time resonance, three types: ordinary, picturing, and total. This is the base sensitivity of these structures, and also the key color of the localization of electromagnetic waves inside the saline water or the fixed layer. So the morphology of the layers is fronting point to research how to ability to open track. The last part of my presentation is a conic crystal umbrella for thermal salination. I use and crowd and go to the the outlines, production, solar salination, and salination is energy intensive, and finally overcome the water energy mix. Water energy mix. Solar energy consumption here. We have a huge amount of electromagnetic waves that comes from the sun and influence on the Earth's surface. And this has in a single hour, the Earth absorbs more energy from the sun than interhuman circulation consumes in a year. So sun provided us with a huge amount of energy. And this figure is the electromagnetic wave infinity with waves. We have the huge or high intensity electromagnetic waves in the visible spectrum and near IR spectrum. As we study the solar intensity over the day, solar intensity begins with 0 and increase, and then decrease in the sun state. The optical properties of the water is characterized by transparent invisible light. So the water doesn't absorb any electromagnetic waves in the visible spectrum. So we need to sense that electromagnetic wave is divided into two parts: shorter wavelengths and longer wavelengths. The shorter wavelengths are ultraviolet and visible, and longer wavelengths is infrared. The optical properties of the water absorb longer wavelengths only and doesn't absorb any shorter wavelengths of the ultraviolet and visible. And this ultraviolet and visible spectrum is high intensity from the solar spectrum that comes from sun. So we need to change or convert the shorter wavelengths to longer wavelengths by using photonic umbrella. And this is the core of my presentation. The contribution in water discrimination training. The object of this paper, firstly, we convert the shorter wavelengths to longer wavelengths in the range of infrared radiation. And the second object is the localization of thermal energy on the starting water system. And this is the structure of two-dimensional solid crystal that flows on the upper part of the water, and here is starting water and this light blue. Modeling and simulation. As the modeling and simulation, we have two parts. The first part is transferring electromagnetic waves into thermal energy. To transfer electromagnetic waves into thermal energy by solving this equation, we achieve the shifting solar radiation to mid-IR and larger wavelengths. And then the efficiency of the system with umbrella. Umbrella depend on its absorption and emission of the umbrella, which absorbs electromagnetic waves. In this figure, we have a water sample surrounded by acrylic walls and 0 signs of illumination. So we don't have any transmitted electromagnetic waves. But after 1 hour of illumination, the electromagnetic wave is spread through this thickness. And if we study the relation between the average temperature of the water surface and time by changing the instant hour, we have the temperature of the surface water is increased as increased. So, with photonic crystal umbrella, the photonic crystal, as we discussed previously, converts the electromagnetic waves with shorter wavelengths to longer wavelengths. So, it will be localized, the electromagnetic wave on the surface of the water. So, the water will be faster than the other cases in heating. And in this case, the time as a average temperature as a function of time with heat flux is we reach to 70 degrees centigrade. after 1 hour of illumination. Different dimensions. The time and average temperature with different types without umbrella and with one-dimensional sonic crystal and with two-dimensional sonic crystal. So, as we discussed previously, we need two-dimensional sonic crystals because the support for the structure allows the vapor to flow up. And the difference between these two figures is the dimension of or thickness of the layer from PIN and EIO2. So we can say that solid crystal solar umbrella is a promising candidate for economically ordered illumination device. Summary and conclusion. Firstly, we design structure from porous Theorem shape and absorption is reached to 95%. And then we design ceramic sensor based on crystal and scan resonance with high sensitivity. And finally, the solid crystal umbrella put on the surface of the water and raise the temperature with high sensitivity after 1 hour. Thank you for your attention.
Yeah. So good evening for everyone. I am Yahya Shergi from Boumerdès University in Algeria. Today I will present my work, which will be about linear density of zinc oxide rock-set structure under isobaric and isothermal ensemble in molecular dynamic prediction. The aim of this work is to know the impact of different temperature and the pressure on linear density and the radial distribution function to confirm the phase transition. It means to find the neighbor atoms, the density, the coordination number, and the band length between the atoms of zinc oxide. We will start with an introduction. There is molecular dynamics, linear density and radial distribution function, rock-set structure, results and discussion, and finally the conclusion. We start with molecular dynamics of simulation. Here we do the experiment on computer. Our computer here is the Raven computer of Cardiff, supercomputer Raven of Cardiff University. The main objective is to find the macroscopic properties from microscopic properties using physical statistics. Here we model the interatomic interaction by a special potential. For short range, we use Buckingham potential, and for long range, we use Coulomb potential. For linear density, and what it means linear density is the measure of quantity of any characteristic value per unit of length. For example, linear mass density is the amount of mass per unit length, and the linear charge density is the amount of electric charge per unit length. The term linear density likewise often refers to linear mass density. It means the total mass over total length. We can use also linear density as atoms per nanometers. For radial distribution function, the main objective of this function is to describe how density varies as a function of distance. The density will be rho GR, where rho equal N over V, and GR is the radial distribution function. Our structure here, it will be Roxelt, is one structure from the structure of zinc oxide. Our system is formed from 5,832 atoms of Roxelt. The parameters of unit cell are A equal B equal C, it means cubic, which equal 4.271 angstrom. For unit cell of zinc oxide Roxelt type, there is 8 atoms. This will be for zinc oxide. We have Roxelt, zinc oxide, zinc blend, quartzite. Today, we focus on Roxelt type, and there is a phase transition between quartzite to Roxelt and to zinc blend according to the value of temperature and pressure. Here we start to see the per atoms of zinc, 2 atoms of zinc of unit cell. We use a range of temperature between the range of temperature is 300 Kelvin. It means that there is an isothermal ensemble. We fix the temperature, and the range of pressure, it will be between 0 and 30 gigapascal. Here we can see the peaks. What it means? It means that the structure is crystal. If the peaks will be like a curve, it means an amorphous structure. For example, we start here with 0 gigapascal and 300 Kelvin. We can see this, the first peak, which give the radial distribution function, or it means the probability to find an atom near from the origin, or it can give us also the linear density of atom of zinc. If we increase the pressure till 1.5 gigapascal, is the blue one, approximately we have the same variation, because approximately we have the same value of pressure. If we increase another time the pressure till 25 gigapascal under the same temperature, it is the green one, is here approximately the same variation with 30 gigapascal, and the black one is under 10 gigapascal. Here we have not a crystal. It means here there is a phase transition, maybe between Roxelt and quartzite, or Roxelt and zinc blend. So what we can see here, that each time when we increase the pressure, we increase the probability to find an atom near from the origin. Also, we increase the linear density. Here we choose another pair of atoms, for example, between 2 atoms of oxygen. The range of pressure, it will be between 0 and 80 gigapascal. We use 2 different temperatures. The first one is 300 Kelvin. The second one is 3000 Kelvin. And we will see what is the effect of pressure and temperature on linear density and radial distribution function. Here, for example, this one, it will be under 0 gigapascal, and 300 is this curve. Here there is a crystal because the existence of this peaks. If we increase the temperature, for example, here under 10 gigapascal and 3000 Kelvin, we can see it will be this one. We can see here the probability to find an atom near from the origin is decreased dramatically. Also, the linear density is decreased, and the structure becomes amorphous because we have not the pixels become like a curve or curved. It means we have not a crystal structure. The same approximately under 20 gigapascal, 30 and 80 gigapascal. If we use another range of pressure for the pair of atoms of between an atom of zinc and an atom of oxygen, we use the range of pressure between 0 and 80 gigapascal, and we choose two temperatures, 130, 100, and the second 3000 Kelvin. For example, the black one, it will be the linear density between an atom of zinc and an atom of oxygen in the unit cell. The pressure here is, it will be 0 gigapascal, temperature 300 is the black one. You can see here the peak means that the structure is a crystal. Approximately it is ambient condition. If we increase the temperature, for example, till 3000, and we use 10 gigapascal, is this one. We can see that the probability to find an atom near from the origin is decreased. The linear density is decreased. The structure becomes an amorphous type. If we increase another time the pressure till 30 gigapascal under the same range of 3, under the same temperature, 3000 Kelvin is the blue one. Approximately we have variation. If we choose another pair of atoms, for example, between two atoms of zinc, we use low pressure, means 0 gigapascal, 10 gigapascal, 20 gigapascal, and we increase the temperature till 1500 Kelvin to see what is the effect of temperature on the probability to find an atom near from the origin, about the distance between atoms, and about the linear density. We can see here it's clear the effect of temperature, which change the structure from crystal to amorphous. We can see also there is a decrease in probability, decrease of. Here we use another pair of atoms between zinc, atom of zinc, and an atom of oxygen. We use another range of pressure between 0 and 20 gigapascal to
Hello, everyone. My name is Somnath Biswas. I am a postdoctoral researcher at Princeton University. Thank you very much for inviting me in this webinar. Today I'll be talking about the movement of electrons in solar materials, particularly for the case of metal oxide semiconductor. And I'll be talking about the use of XUV reflection absorption spectroscopy to track the motion of electron in solar material. So before I go into the detail of the talk, first I would like to show you how solar energy research is important, why solar energy research and the development of XUV spectroscopy, which is in the ultra fast time domain, time resolution. And I'll show you one example that we understand the electron dynamics in one of the solar material in this case. So before I go into the detail of the instrument, I'll just briefly tell you the solar energy research, importance of solar energy research. And this is very important because it's a tremendous source of untapped renewable energy. The energy associated with the total oil content of Earth is equal to the energy that sun can deliver in Earth in 1.5 days. The amount of energy that human annually uses, sun can deliver that amount in just 1 hour. And the recent data suggests that having all these advantages of solar energy, the recent data suggests that we use only 0.6% of the total energy for practical application. And if we calculate the conversion efficiency of the solar energy conversion, we see that the efficiency is very low. It's on the order of 10 to the power 6. So that means most of the energy is simply wasted, and there's a lot of scopes to improve the performance of solar energy research. This is the data from Google Scholar citation to show how relevant is the solar energy research. So you can see that millions of research paper and patents are coming out related to the solar energy research, and the number is keep growing over the past few decades. This represents that solar energy research is a very active area of research and has a great potential to discover untapped energy, which can be tapped from solar energy. So here I am just showing a cartoon diagram of how you can convert solar energy to the form of electrical energy. So in a typical solar cell, you have a heterojunction of two different semiconductors, semiconductor 1 and semiconductor 2. And when sunlight shines on one semiconductor, it produces a strongly bound electron and hole. So it's a bound electron and hole. Then after that, the next step is the exciton dissociation, where the electron in the conduction band of semiconductor 2 travels at the interface. And then the next step is the charge transfer process, where the electrons goes to the semiconductor 1. And if you connect this to an external circuit, so directional movement of electron will produce electricity. And that's how you can convert solar energy to the form of electrical energy. So now, in a similar way, you can convert the solar energy in the form of chemical energy. For example, here is a heterojunction of semiconductor 1 and 2, the photoexcited electron, let's say in semiconductor 1, this electron can be used to do the reduction chemistry, and can be used to do the oxidation chemistry. And this process happens in our plants, and that's how we can convert the solar energy in the form of carbohydrate that happens in our plants. And nature has designed this very efficiently. So there's a lot of research going on to mimic the process of nature in the form of artificial photosynthesis, so that you can have material which can mimic the artificial photosynthesis process and can convert the solar energy to the form of chemical energy. But one of the major challenges for this conversion from the solar energy to the chemical energy is the electron dynamics, like how the electron movement happens within this solar heterojunction material. And it turns out that after you excite electron from the valence band to the conduction band, you have this strongly bound electron and hole that I just described. However, there are certain instances where this electron and hole recombine and the energy is simply lost before it can be transferred to the other part of the semiconductor and do some useful useful chemistry. So this is a major challenge, and this sort of things happens very fast within few hundreds of femtoseconds. So you need to have to understand these processes, you need to have the ability to probe such exciton dissociation and recombination processes with femtosecond time resolution. Another detrimental effect that could happen in the material is the material defects. For example, in lattice, here I'm showing a lattice diagram of nickel oxide lattice. And in this nickel oxide lattice, move one oxygen. So you have this defect side, which can also induce this charge recombination, which can also reduces the efficiency of solar material. So there are other kinds of defects as well in material, for example, grain boundary defects. So this can also act as a detrimental effect for solar energy conversion. So it is very important to understand how this defect mediated process happens. So my research sort of address this defect mediated electron recombination chemistry and hole transfer processes with very fast time resolution and element specificity. I'll tell you why element specificity is important. So this is a cartoon diagram of water oxidation reaction. Okay, so here I'm showing that after creating the charge carrier, let's say you create this positively charged carrier hole, which goes to the reaction center at the anode to do some oxidation chemistry, let's say water oxidation. However, during this journey of this hole, there could be various defect site and trap site, like I just discussed. But there could be understand how this charge carrier travel to this defect site, trap site, and active site so that it reach the reaction center and do the oxidation chemistry. So for this reason, it's very important to site selectively probe these processes. So you need to have a technique which can probe these processes with site selectivity. And also in the solar heterojunction that I just described, the mechanism could have happened in two different mechanisms. So in the case one mechanism, where you excite the electron in semiconductor 1, and then you have this strongly bound exciton, and this exciton dissociate to create free electron and hole, and the hole transfer happens on a later time scale. So it's a two-step process. The first step is the exciton dissociation, and the second step is the hole transfer. Now, in a second case where you create this bound exciton, but this bound exciton doesn't dissociate, right? And it only dissociates when it reaches the interface, and the dissociation of this exciton and hole transfer that happens simultaneously. So it turns out that if it has happened through case 1 mechanism, then the efficiency of the solar energy conversion is very high compared to the case 2 mechanism, because in case 1 mechanism, you could have long range energy transfer and tunneling of the charge transfer, which doesn't happen for case 2. So these sort of processes are very challenging to probe in case of transition metal oxide, because their valence band is highly hybridized with oxygen 2p and metal 3d. So you will really don't know that what you're probing using this if you use an optical spectroscopy. And for example, if you use optical spectroscopy, then it's very difficult. So my research goal is to understand such processes with site selectivity and femtosecond time resolution, so that we can remove this detrimental effect and improve the solar energy performance. So now I will discuss about the development of XUV spectroscopy, which I developed in my doctoral research to understand these processes with site selectivity. And the site selectivity is important, as I discussed, because the optical spectroscopy, in optical spectroscopy, you see this broad absorption spectra, and there are many multiple transitions which is underneath this broad absorption spectra. So you will not know whether it's a charge transfer transition or whether it's a DD transition because of this broad. So that's why you need some technique which can produce very specific transition, for example, extra absorption spectroscopy, because extra absorption can probe core to valley transitions, and core electron energy are very high. So it can provide the fingerprint of the element in a material. And also, in addition to the element specificity, it can provide you the oxidation state sensitivity and the spin environment and geometric environment specificity, and which is very important for solar material, because when the charge transfer happens, it reduces or oxidizes the material. So if you have X-ray transition, if you probe with X-ray transition, then you can really probe with element and oxidation state sensitivity. So in a way, you can really probe the very localized state or the charge localization. And of course, you need to have the ability to do these experiments with very fast time resolution. And this is what the concept of ultra-fast spectroscopy comes, motion of the apple falling. So you need to take the snapshot of each of these processes with real time, right? So you can produce this molecular movie in sort of molecular movie, and the pump probe spectroscopy is a very nice approach to probe these processes with ultra-fast time resolution, because you cannot do this process with a normal camera. You need to have ultra-short pulses because no electronics can probe these processes the ultra-fast resolution, because this is hundreds of femtosecond. So just to give you an idea how fast femtosecond time is, femtosecond is a millionth of a billionth of a second. So let's say in 1 second, light can travel around the Earth almost 8 times, but in hundreds of femtosecond, light can travel only the diameter of the human hair. So femtosecond is that fast. So this process needs to be probed with femtosecond time resolution, as the exciton recombination and the transfer happens that fast. And also you need to probe with site selectivity. So the only way you can do these experiments is using a synchrotron sources where you have the site selective processes. You can probe. However, the problem here is that you need to have the beam time in a synchrotron layer. Here I'm showing an example of APS, Advanced Photon Source at Oregon National Lab. You need to have the beam time to do the experiment, and then you need to have the ultra-fast time resolution, which is 80 picoseconds. So the processes which is faster than 80 picoseconds, you'll not be able to probe with this. So in my doctoral research, I was involved in designing an experiment, which is an instrument, which is like a synchrotron in a laboratory. So basically here you can get all the advantages of X-ray spectroscopy, like element oxidation state and ultra-fast time resolution. In additionally, you can get the time resolution which is faster, like 55 femtosecond faster. And we can also get surface sensitive information in reflection geometry. And this is very important because all the catalytic reaction and chemical reaction happens at the surface of material. And if we can probe these processes with surface sensitivity, we can get really surface sensitive catalytic information, the surface sensitive electrodynamical information. So this is the diagram of the instrument. So this has 3 parts. The first part, this is where we generate the XUV. So it's extreme ultraviolet, you can say, or you can say like in the X-ray domain, we generate electron around with energy between 30 to 72 electron volt. So that is used to probe the metal oxide semiconductor electrodynamics. And we have a separate beam line for pumping the system, so from light. So we excite the material with this pump and we probe with this X-ray, right? And then we have a detection chamber where we have a grating. So this is the sample. Here is the sample. The XUV beam reflect of the sample and produces on a grating, and from the grating to the CCD detector. So that's how we detect the X-ray. So the way we generate the XUV in this system is a process called tunnel ionization. So basically what happens in the gas cell, this gas cell is filled with a helium gas, let's say noble gas. And what we do is a strong field ionization of this noble gas. So 800 nanometer laser source, which is about 2 millijoule. We focus down to this gas cell, and the intensity at the gas cell is about 10 to the power 14 watt per centimeter square. So it can distort the atomic potential. It's in the non-perturbative regime. Through this distortion, the electron can tunnel ionize through this forth in the laser field after it tunnel ionization. But as the electric field oscillates back and forth, when the electric field reverses sign, the electron comes back to the parent ion. When it comes back to the parent ion, it produces coherent ultra-short attosecond burst of XUV pulses. And that XUV is used to probe the sample. And this is surface sensitive because we are reflecting the XUV probe in a grazing incidence, which is 8 degree. And at this 8 degree, you can get the probe depth of about like 3 nanometer. And that's why you can get surface sensitive information. So when these XUV pulses are reflected off a silicon substrate, we get this high harmonic combs which spans from, and when, let's say we have a metal oxide catalyst, iron oxide, when it is reflecting off iron oxide, we have a dip at around here. So this is at around 55 electron volt, and that corresponds to the iron 3p to 3d transition, right? So let's say in a traditional X-ray absorption spectroscopy, you probe oxygen 2p to iron 3d transition, that's an LS transition. But here we are probing MS transition from the metal 3p to 3d. So that's an image transition, and we can get still element specificity information. But just to show you that this spectroscopy can probe the element specific information, here I'm showing all the capabilities together. For example, here I'm showing the XUV reflection absorption spectra from titanium oxide to nickel oxide. And you can see that as we move from the periodic table from the left to the right, the 3p to 3d binding energy increases, and we get specific information for element. So it's an element specificity. So it retains the element specificity of extra absorption spectroscopy. It can provide the information of the oxidation state sensitivity. So basically, if you have, for example, Fe2+ or Fe3+, it can provide distinct spectral signature. So you can get the information with probe depth of 3 nanometers, so which is a surface specific information, which is very important for catalytic material. And also, we can get information with ultra fast time resolution. Here I'm showing an instrument response function for this material, and then you can get the instrument resolution time of about 55 frames per second. So basically, we can get all the benefits of X-ray spectroscopy along with the ultra fast time resolution. So I have shown you how we have developed the XUV spectroscopy and the benefit of XUV spectroscopy. Now, for the interest of time, I have done many different experiments and many different development and measurement on electron dynamics, surface specific electron dynamics, for example, in iron oxide, in nickel oxide, in heterojunction. Particularly for this talk, I have chosen the heterojunction example because that's real. You can mimic the real solar material here. And I'll show you how XUV spectroscopy has been used as an element-specific technique to probe electron dynamics in a solar material, right? So I'll just give you one example, but if you are really willing to learn more about this, you can visit my Google Scholar profile to get an access to all the other papers that we have published. So as I mentioned that the electron transfer or hole transfer, this process could happen via two different mechanisms. One is the case one, where the bond, you dissociate the exciton very fast, and it happens after the step process. Now in a case two mechanism where the exciton dissociation doesn't happen, and then the exciter one step process. So my goal was to understand how this case one and case two mechanism, what is happening in a solar heterojunction. All right. So for this, I choose a material heterojunction of nickel oxide and iron oxide. So before I do the time resolved measurement using XUV, I did the ground state measurement of each material, each pure material. And you can see that for the iron oxide, we have a specific image transition, which is at 55 electron volt. And if you have only nickel oxide, we have a transition at around 65 and 68. And this is because of the spin orbit coupling in nickel oxide. We see these two features. Now, if we put a thin layer of nickel oxide, it's a whole transport layer on top of iron oxide. Now we can get signature of both iron edge and nickel edge simultaneously. And this is where the magic happens, because here now we can probe the whole transfer between the iron oxide to nickel oxide layer with element specificity and frame per second time resolution. So before we do the photo excited measurement on the heterojunction material, I did measurement on pure material. So this is the data for only pure iron oxide. So what happens is when you excite the electron in the iron oxide layer, it's an iron 3+, right, in the ground state iron oxide. So what happens is the electron transfer happens from the iron oxygen to iron, reduces to produce iron 2+. So we see this is the time resolved XUV data. This is the x-axis is the energy and y-axis is the time. So it's ultra fast time when you can see 0 to 20 with a 400 nanometer light, which is about 3 electron volt. We can excite the iron oxide layer and we get state absorption of the iron 2+. That means the charge transfer state is producing. So electron is on the in the iron and hole is on the oxygen, right? But I did the same experiment for nickel oxide and I did not see any change. So basically nickel oxide doesn't have any transient response at this particular wavelength. So it's a good sign, because now if we put the nickel oxide layer on iron oxide, if we see any transient signal in case of nickel oxide, that will be solely because of the charge transfer, because otherwise we should not see any signal in nickel oxide, right? So this is the data for the case of the heterojunction. And for the case of heterojunction, we see that the nickel oxide, only because of the whole transfer is happening in the nickel oxide layer. So after the electron, which is there in iron oxide layer, the iron oxide produces the iron 2 plus, but the whole from the iron oxide layer is now transferring to the nickel oxide. That's why we see the signature of nickel 3 plus, because the ground state nickel oxide is nickel 2 plus, and it accepts and whole. We zoom in at the interface. What is happening is you excite the electron in iron oxide layer, and the electron is localized in the iron oxide layer, where the whole is transferring to the nickel oxide layer. And we are able to see the signature of nickel 3 plus, nickel 2 plus, iron 2 plus, and iron 3 plus. So you see how XUV spectroscopy has been used to probe the element specificity of the charge transfer process, and with oxidation sensitive resolution, right? You can probe selectively whether it's a nickel 3 plus or nickel 2 plus. But again, our interest was to find whether it's a one-step process or two-step process. So what I used is a kinetic model to understand this process. So in this kinetic model, you excite the electron from the ground state to the bound exciton state, and then from bound exciton state to, let's say you have an intermediate state, which is the dissociated exciton. It's a charge transfer state. You have calculated the population as a function of time using the differential and integrated rate equation. And we see that using this model, the simulation of this model can relatively nicely reproduce the experimental data, right? So that matches very nicely. And we have also tried with one-step process, and it doesn't happen. The simulation doesn't predict the experimental results. So that means it's a two-exciton dissociation happens ultra-fast timescale, so about 680 femtosecond timescale, and the dissociated exciton produces in a later timescale with 9.2 picosecond. So that means it's a two-step process, and it's a highly efficient process. As I mentioned, that the two-step process will be a highly efficient process, right? So again, to conclude this study, I'm saying that the hole is localizing to the nickel 3D valence band, where nickel produces the nickel 3 plus, wherever the electron is localizing in the iron center. So this is a model heterojunction case where we studied the electron and charge transfer, the whole transfer processes with element specificity and oxidation state sensitivity. So the implication for this research, we're developing this highly novel laboratory-based XUV absorption technique, where you can do all this measurement in a laboratory instead of going to the synchrotron. Also, you can screen the solar material very fast by doing this experiment, and you can provide the design parameter of how you can improve the solar cell efficiency for this different processes. And for in the future, like in Ohio State, we're developing a national user facility based on this technique, where we can get attosecond time resolution, and we can really understand and control the energy flow in solar material. And NSF, we got a fund from NSF to establish this national extreme ultra-fast science facility at the Ohio State, and it will be a historic first for the United States. And really looking forward to have this user facility so that people from different countries can come and do experiments here. This was mostly my PhD research. Right now, what I am understanding is the electron and spin dynamics in quantum material. So, in quantum material, electron spin can be think of as a qubit. So the building block of quantum bits. So that's qubit, and it can, by superposition of two spin state of a molecule or of a material, you can have several different qubits, and you can entangle different qubits to advance the modern development of modern quantum technology. And I'm currently working on that. I will in a future conference, I'll probably present on this data, which is not published yet. And I hope you have enjoyed the talk, and I'd like to thank the organizer for inviting me, and thank you so much for your attention and listening to my talk. I would like to acknowledge my group and the funding sources for funding this research. And unfortunately, I was not able to attend this seminar in person. However, if you have any questions, please email me. My email ID is Somnath, SOMNATH @princeton.edu. So if you have any question and any comments and suggestion about my research and my future direction, I'll be happy to discuss and take any questions. Again, thank you so much for inviting and listening. And this is where I'll stop my presentation. Thank you so much.
Yes, it was a presentation from Dr. Somnath.
Hi, my name is Hassan. I'm Professor Reimer's postdoc, and I'll be presenting on his behalf today.
Okay, thank you. Thank you for letting me. We were trying to contact Professor Reimer.
Oh yeah, so unfortunately, yeah, I was informed not very long ago, so and Professor Reimer couldn't make it today, so he apologized, and I'll be doing his presentation today. So thank you. Thank you for organizing this webinar. And again, as you probably know now, I'm not Professor Reimer. I'm a postdoc in his group. My name is Hassan. And I'll be giving the talk today. And the title of the talk, as it indicates, is based on our ability to control light and matter interaction in nanoscale through the use of semiconductive nanomaterials. So for today's talk, I'll start with giving some background about why we're interested in using these materials in terms of applications, and some general knowledge based on how the semiconductor nanowire type technology was evolved. And I'll discuss how we took advantage of the semiconductive nanowires to realize highly absorbing metamaterials. And finally, I conclude the presentation by talking about the opportunities in terms of applications that is ongoing in our group and our research team. So basically, the motivation is to address the growing demand for detectors that have very sensitive, very high sensitivity, to the point that we can detect very low light intensities at single photon regimes. And some of the applications that our group is interested in essentially are listed here, such as biomedical research, where we could do dose monitoring for cancer treatment, single molecule detection in quantum sensing. Also, there's a huge interest and demand for quantum communications, for secure communications and between the over large distances, as well as creating a LiDAR system to be installed in the satellites, as well as creating quantum LiDARs, which has potential in defense and military applications. And so our goal is to use our technology, that research we have, to create a technology which is essentially become a single photon detector. And we're hoping that our detectors can also operate at the close to room temperature. So the idea of using single nanowires as a nanophotonic devices is dated back to over a decade ago, where scientists across the globe studied these nanowires, and they tried to theoretically and experimentally show what are the interaction of light with these nanostructures made of semiconductor materials. And I could think of two general classes that these materials could operate under. One would be where the light interacts with the materials, where the cross-sectional materials is where the incident light interacts with initially, and where the wave vector of the light would be parallel to the axis of the wire. And the second class and category would be when the light interacts with the wire at incident angle, which is perpendicular to the axis of the wire. In that case, we are exciting different modes inside the wires. So essentially, these two, when we're taking advantage of cylindrical shaped type wires, what we could think about is mostly the devices that they could operate at a relatively narrow band resonant, which can be tuned to the resonant frequency that is supported by the wires. But if you're interested in the broadband response, the nanowires, simply by creating tapering angle to the wire, we could create a continuum of radii, which could now support the variety of different frequencies at resonance with respect to the cross-section of the wire. And we could now create a periodic structure, which then allows us to generate a broadband absorption capability with high absorption efficiencies. Another approach would be to create a periodic structure and use cylindrical features with different radii. And by identifying a unit cell, which comprises of series of these different nanowires, we could now control the broadband absorption property of the material as well. So as this image shows, so one interesting fact about such approach would be the light that resonantly coupled into the wire would essentially be supported by the wire, but those frequencies that cannot be resonantly interacting with the wire would be scattering, which then could be collected by the adjacent wires that are supporting the frequencies. So based on the mode of operation, we could think about how and study how these configuration lead to excitation of optical modes inside the semiconductor nanowires. And how it's been done, and it's been shown before, is simply by solving Maxwell equation for cylindrical boundary conditions for infinitely long wires. What we need to pay attention is the beta term, which is the Z component of light inside the wire along the y-axis, which is angle dependent, and it kind of tells us what type of mode we expect to excite based on the interaction of light with the wire. So in case of having a 90-degree angle of incidence, the term basically tells us this term becomes 0. So what the mode that we are expect to excite inside the wire would be in form of pure T or pure TM. And by introducing angles that they're not 90 degrees, the beta has a value which then defines the modes that gets excited. There are in terms of mode, which we expect to have hybrid modes of electric and magnetic fields. But interesting fact about that is we could now study these, and we could also understand how the light interacts with the material as it gets coupled. So the mode that excites inside the materials in a guided form, and it's also known as a leaky resonant modes inside the wires, which means it has a strong tendency to interact with the surrounding material. So it has a tendency at the interface of the material and air. It scatters out into the free space, which is going to, in my later slides, I'll show that we are actually trying to take advantage of multiple of these modes to achieve a broadband absorption capability at near unity. So since we can control the light matter interaction by simply shaping the structures, by creating a lattice structure made from these materials, we could realize a metamaterial. And as we all know, metamaterials essentially are artificially engineered materials, which we could use for introducing a very exotic optical effect that cannot naturally be experienced. So this is exactly what we're doing. We're using semiconductor nanowires for creating highly absorbing materials. So in our approach, in our group, we're looking at two different flavors of metamaterial absorbers. One would be the narrowband absorbers, and under this category, we're working on two different subsection. One would be the structures are based on the Mie resonances, where we control the height and the diameter, which essentially gives us shapes such as the nanodisk. And these Mie resonators, they are very sensitive to local refractive indices, and but essentially we could use them to get a relatively narrow band response. Alternatively, we could create a slightly bit broader band response through cylindrical nanowires. And these nanowires, the advantage that they have compared to Mie resonators is they're not as sensitive to local refractive index. And if you're interested in broadband response, as I showed earlier slides, we could introduce tapering angles and create these truncated type nanowires, which now support a variety of different frequencies. And we could incorporate these in a lattice structure to realize our metamaterial absorbers, which has a broadband response. So I would like to quickly get into slight more details about how the Mie resonators work. So what we do is with the Mie resonators made of semiconductor materials, we are trying to induce a Kerr effect, which essentially means we are trying to tune the resonant frequency for magnetic and electric dipoles in a single structure to occur at the same frequency. And at the point that they overlap, we could control, we are basically suppressing reflection. And at that point, our material is basically we could confine the field inside the material, and the probability of generating charge carrier will increase. And so I'm showing that this is the radii sweep and the height sweep. We could actually show that we could control the dipole response of the electric and magnetic field, and we can control it at point that they cross each other. And this is where the maximum absorption frequency can occur. So alternative to this approach, we could generate Kerr effect by controlling the dipole responses between the two structures. So essentially, we're talking about the lattice resonances that arises from the electric and magnetic dipole moments that is generated between two structures. And by controlling that, we could also create Kerr effect that is now created by the lattice itself. And again, at point that the frequency that the both magnetic and electric lattice resonances overlap, we are experiencing almost no reflection. And so in our approach, what we are doing is we're basically generating Kerr effect by tuning the nanodisk dimension and also inserting in a lattice structure and controlling the lattice resonant modes for electric and magnetic dipoles to the same frequency that is supported by this single structure, and that way we are trying to increase the absorption efficiency of our materials. I need to comment on the fact that our approach we're mainly based on the indium gallium arsenides because of the broadband responding has over a broader wavelength, and therefore most of the work that we've done and simulations and modeling as well as fabrication is based on this material. And so allow me to show how the light interacts with the Mir resonator type structures and what we expect to see. So as the light interacts, it gets trapped, and we see this swirling and the resonation of the field inside the wire. And this is essentially what we expect to see, which doesn't allow light to be reflected as we're operating within this Kerr effect realm. So alternatively, what we could do here is create cylindrical nanowires, which, as I mentioned, the advantage of using cylindrical nanowire is less sensitive to local refractive index of materials that the nanowires could be embedded in. So how we can do this is by controlling the diameter. We could essentially create features that are supporting frequencies as a single mode response inside the wire. But as we increase the diameter of the wire, we are essentially allowing more modes to be coupled and excited. And so at some point, we see that there are more modes can simultaneously excite within the wire, and therefore we're expecting the broader band response. However, if you were still interested in a single mode and broadband and high absorption efficiencies, we could simply choose the diameter carefully and insert it in a lattice type structures. By tuning the separation carefully, we could now create arrays of cylindrical type nanowires to realize metamaterials with a relatively high efficiencies, basically almost close to unity. And that at least modeling suggests that we are capable of doing that. And so how we are achieving this and what is this mechanism behind the enhanced absorption, what we believe that is occurring at this point is as the light couples into the wire, we are generating resonant modes in form of hybrid electric and magnetic field inside the wire, but the leaky nature of the modes inside the wire leads to the scattering into the free space, and that would be coupled in by the adjacent wires, which leads to excitation of the pure T or TM mode, as I showed earlier, based on how the Maxwell equations be satisfied. And by putting the structures at a specific distance, we could now create regime that is resonantly support those scattered leaky modes. Therefore, we can expect to observe a near unity absorption within our material. And so here is how we could expect to see simply the cylindrical structure interact with light. And as you can see here, there is a strong interaction between the wire inside the wire and outside world, and the leaky modes was shown to be scattering very effectively. So as the light gets coupled into the wire, there's a tendency to immediately get traveled down as it travels down the wire towards, gets traveled also towards the interface and leaks out. So as if you're interested in the broadband absorbing metamaterials, truncated nanowires could be a good solution. And so our approach to realize a broadband metamaterial absorber was by tuning the cylindrical structure to the band edge of our material, so in gas around 1650, where we still experience a single mode resonant response. And systematically, we increase the bottom diameter. So this is the response of a cylindrical wire. Systematically increasing the bottom diameter, we're observing more modes could be coupled and more frequencies could be essentially supported by the single nanowire. And once we got the optimized relative top and bottom diameter, what we could do is grab that cone type structure and insert it in a lattice type feature. And by controlling the separation of the structures, we can now see how the absorption efficiency could be altered. And at the specific and optimum position, we observe that we have a near unity absorption efficiencies. And this is what we expect to see experimentally as well, as I show in later slides. And as separation becomes larger, as we can see here, the absorption efficiency drops. Another interesting fact is that supports our model data is the scattering efficiency, which means as we increase the separation, more light gets to be scattered, and the absorption efficiency of the material overall continues to drop since the scattering starts to increase. And here we can see the electric and magnetic field and how they operate for this is for one wavelength around 1100. As the light interacts with the material, it has a strong tendency to leak out and interacts with the edges and wires. And we also observe the magnetic dipole coupling between two edges and structures. So here's the mode that we can expect to see in a single wire as this is a broadband source, and most of the light could be supported within a single structure, as I showed in the previous slide. And this is how we expect to for light to travel down the wire. So we went further. We actually did fabrication, make these structures through nanofabrication processes that has been optimized in our group, and we managed to create these uniform cylindrical, the truncated nanowires made of indium gallium arsenide. So to put in perspective how the absorption efficiency is modified, we looked at the indium gallium arsenide with a thickness of around 2200 nanometers, which is essentially the film that has been grown on top of indium phosphide substrate. It's actually grown film. And this is the absorption. The red trace shows the experimentally absorption efficiency of the planar film. And upon creation of the nanowire structures, the red trace on this graph shows how much absorption we can achieve. It's above 90% over a broad range of spectrum. And the simulation, which is the blue solid line, shows that our absorption essentially is experimental data has a qualitative agreement with our model data. So we expect the material have a broadband absorption ranging from visible all the way to near infrared region. And this is, again, another motivation of using indium gallium arsenide. And so it's experimentally might be a bit challenging since we have indium phosphide film underneath, and we're using FTIR to measure the absorption property of material. So therefore, it would be at some point we'll be operating within the band gap of the indium phosphide. Therefore, experimentally might be a bit of a challenge. But we could see here, this is just a microscope image with a high intensity light. This is the indium gallium arsenide substrate surrounding the array. As you can see here, the material, the nanowires are highly absorbent within the visible range. And this is a scan electron micrograph of the nanowires, which we can now fabricate over a broad range with a very uniform shape and property. So the opportunities that we're trying to exploit these nanowires for actually is in creation of single photon detectors. So our early attempt to create a single photon detector or detectors with a sensitivity at a single photon regime was done a while back using indium phosphide materials. And there was a collaboration work with Eindhoven University. So we managed to create these truncated structures to create these highly absorbing metamaterials with a broadband absorption within the band gap of the indium phosphide. And we successfully showed that we have a relatively high external quantum efficiencies, and also the sensitivity of the material and detector that we created, made of the nanowires of indium phosphide, are basically within the single photon regime. So as we increase the number of photon per pulse, we're using a pulse laser to excite it and generate photocurrent. As we increase the number of photons per pulse, we can see here there's a completely noticeable difference between the photocurrent generated based on the pulse number of photons. And we extract the internal quantum efficiency within the structure is about 73%, and the multiplication factor is measured to be around 10 to the power of 10 to the fifth. So another interesting fact about such a detector is made of the semiconductor nanowires, and in this case indium phosphide, was that they have a very fast response. It's around 1.2 nanoseconds, which is now comparable to standard some of this state-of-the-art devices that have been commercially available in the market. And here's in comparison of different single photon detectors. So silicon detectors are really providing us with a relatively high efficiencies, but unfortunately they have a limited detection of band as we go towards the longer wavelength. So alternatively, we are interested in near infrared region. The indium gallium arsenide type detectors could be ideal, but they suffer from a low detection efficiency. So the highest efficiency type detectors for single photon would be the superconducting nanowires, but the downside of the use of these devices are essentially is the cryo system and an ultra cool temperature they need to operate under. What we expect to see now is the use of our approach in generating these nanowires and turning it to a detector, which could potentially operate at the room temperature, but the response of our devices are now at this point, based on our measurements, comparable to superconductive nanowires. So the timing jitter is about, it's less than 20 picoseconds, which is comparable to timing jitter of the superconducting nanowires within the similar dead time response that we are measuring. So by incorporating InGaAs, we are hoping to show that this device could in fact be a broadband detector that ranges from UV all the way to near infrared, and that is the goal and motivation behind the use of material, the 3.5 material that we have. So in summary, I hope I convinced you all that we have, through nano fabrication, we could create the structures with precise control over the light and matter interaction. Semiconducting nanowires are interesting for the use to generate these resonance type structures, which will control the light and matter interaction based on the ranges through spectrum. And so we could create essentially the narrowband or broadband response type detectors, and by controlling the spectral range, we can create detectors that they are sensitive and operational and different for different applications. We show that we could create high absorption absorbing metamaterials with our approach, and with operating within the band gap of the 3.5 semiconductors, we could create detectors that they have a very fast response. And we're hoping to exploit all these properties of material and devices that we're making to create a very sensitive single photon detector. And with that, I'd like to thank you all for listening to my talk today. And as you all know, usually the work that has been done and presented by postdocs is often realized by the other graduate students. So special thanks goes to Brock, who's been working heavily on fabrication of the nanowires. Brad is working hard on the electronic side of the devices, which has been helping us to turning these nanowire devices into a detector. And our collaborators at the Eindhoven University, Eric and Joss, and Zabig, who is collaborator working with us at the University of Waterloo for providing us with the indium gallium arsenide films. And none of this would have happened without the funding. So special thanks goes to our funding agencies and the Institute for Quantum Computing that helping us throughout our work. So with that, I'd like to thank you, and I'm happy to answer any questions if you might have.
Yes.
Okay, so this is a presentation focused on a particular wavelength in high-powered laser photobiomodulation therapy, and 1064 nanometers is historically a relatively recent wavelength in photobiomodulation therapy. Some of the earlier work was in the visible spectrum initially in the 630 range, and that continues to be used for hair growth, for example, a lot. And 810 to 850 is used a lot, and 980, but 1064, it has the lowest refraction index of these in some basic studies, and there's some photoacoustic imaging studies that have compared 560 and around 810, and they have shown great depth of penetration for the 1064 in photoacoustic imaging studies. So what we sought out to do here is to explore the outcomes in clinical trials that use this. And one thing that's kind of interesting is that as far as the high-powered photobiomodulation therapy studies, that most of the studies actually use this wavelength, even though if you look at all photobiomodulation therapy studies, which is most of those studies are low power, less than 500 milliwatts, and they don't penetrate the skin much at all, and so they're limited to a lot of medical indications that are more superficial, like leg wounds and oral mucositis, and some nerve pains where the nerves can sort of send their signals to deeper regions. But pain is a very complex pathology to understand. So we, if you see in this figure on the left, you can see in the hard trace shown here, this is eumelanin. So for people who have a lot of pigment, the 1064 nanometer wavelength is good because it's not getting absorbed by the pigment, so it doesn't get as hot for darker skinned people, people along the equatorial regions. Whereas something like the visible light 680 or 810, there's going to be some heat in darker skinned individuals when you do the higher powered lasers due to the melanin absorption. So 1064 has that unique biophysical advantage as well. This trace is the water. And so here we have carbon dioxide lasers, which are used to cause essentially flash boiling and tissue ablation in a surgical setting. I'm just going to start my timer. And so we did a meta-analysis of all the studies that were high-powered photobiomodulation therapies. We excluded many that were not in clinical trials, so animal studies we didn't include. We're looking for outcomes in clinical trials. And we excluded those that were, again, the power is too low, or it was not the 1064 nanometer wavelength, to try to understand what kind of medical indications perhaps are particularly amenable and positively responding to 1064 nanometers. And we found 22 independent studies, many on arthropathies, including knee arthropathies, spine, shoulder, and elbow, and wound, such as cesarean surgical wounds, and endometriosis with gynecological, and osteoporosis with decreased bone density. And they assessed pain as the most common outcome that was assessed, quality of life, range of motion for, and how stiff were these individuals after the treatment versus placebo laser. And there were some studies that measured the thickness of the cartilage. They did ultrasound along several different angles in the knee in a couple of studies. And what they found, what we found is that looking at all these, pain was reduced with a statistically significant fashion in 90% of the study assessments out of 20 that assessed pain. One of the most impressive ones involved 2 weeks of treatment every day for 5 days a week for 2 weeks. And even after 6 months, there was an increase in the thickness of the cartilage in knee osteoarthritis. So I don't know how many of you are aging like myself, but I'm basically bone on bone. And I look at my 10-year-old son who he's like a pogo stick, how much space he has in his joints between his bones. You could see this on an x-ray, but I'm bone on bone. And so to be able to increase cartilage is really exciting, and they reduce the pain and all that. And so the knee is a particularly positive. Knee osteoarthritis really responds well to high-powered laser photobiomodulation therapy. And that's here. Okay. So there was also improvement in wound healing in a burn study, and the bone mineral density was increased. This is a single study, the bone mineral density, so that should be considered some more. And the largest effect sizes we calculated using Cohen's d effect size calculations were in the knee arthritis. So if you can use this therapy to reduce or prevent a knee surgery, for example, you would save tens of thousands of dollars, not to mention the pain aspect. So here we have, within the poster, you can see all the citations for all the knee arthritis studies, the wound studies. I believe there was a burn, and there was a cesarean recovery, and a spine. So that these are some of the most largest effects: arthritis, wound, and back problems. And the settings for the laser were typically, at least for these really the best outcomes, involved 10 watts with probably a spot size of something like 4 square centimeters. So a power density of at least typically at least I think it's at least 3 watts per square centimeter. But one thing that's kind of interesting is that what's out there now is lasers that go as high as 80 watts, but there have not been any, there just haven't been any clinical trials for these. And particularly with transcranial photobiomodulation, there's been some really amazing results with Dr. Robert Hedaya, and used to be at Johns Hopkins, integrative psychiatrist. So they have gotten amazing results with 20 watts. And so when you have these higher watts, you're penetrating into deeper tissues. Yes. So so in conclusion, the 1064 nanometer light, its use in high power laser photobiomodulation, it looks like it's especially useful for darker skinned individuals. There was also a genetic study where I didn't talk about that. They looked at a mouse that didn't have melanin, and there's less heat with the laser. That was a basic study, basic research. And so the practitioners of this this can really be appreciated. So in the context, so if you think of perhaps the most useful setting might be knee osteoarthritis, a knee injury in a dark-skinned individual. That way you can really penetrate deeply and get a positive outcome treating. But really, there's been positive outcomes for frozen shoulder and tennis elbow, metacarpal thumb indications. So it's generally a lot of musculoskeletal. There was some studies on plantar fasciitis, which was a little more challenging for some reason. I don't know if the circulation is particularly challenging down there, but yeah. So with that, I can take some questions.
So yeah, my name is Dovydas Blaževičius from Kaunas University of Technology. I will be closing this conference, and I am a chemist here in Lithuania, and I am responsible for synthesis of new organic semiconductors for OLEDs, organic light emitting devices. So in this work, I synthesized carbazole-based materials which have diphenyl sulfone fragment. And this synthesis were carried off in 3-step synthetic route. So first step was iodation of carbazole via Tucker iodation procedure. And then Suzuki reactions were carried out with boronic acids. And the last step was reaction of our intermediate compounds with the fluorosulfones, and our objective materials are shown here. Sorry, I will maybe select laser pointer, and our and thermal properties of these materials were good. As you can see from DSC thermograms, both materials were fully amorphous with glass transition temperatures of over 150 degrees centigrade. So that shows us that these materials are stable in amorphous layers. So these materials were solvable in common solvents like acetone and THF, which are really important because our main goal of this work was to improve the performance of solution processed OLEDs. And then the work was continued by our partners in Taiwan, and they calculated HOMO-LUMO levels, and they figured out that these materials would be best used as hosts, because the first idea was to use these materials as emitters, but HOMO and LUMO levels were separated. So they decided to use these materials as emitters. So the photoluminescence decay is shown here on the right, with both of these emitters and doped with both of these hosts doped with emitter. And as we can see, the emitter H1 wasn't really good at confining our electrons, and the decay was fast, so there's no delayed component, as we can see. So we can see, sorry, a little bit. Yeah, we can see the device structure. So it's a simple device with TPPI and P.PSS as electron and hole injection layers, and our hosts were tested with a carbazole-based green emitter, and by changing, and we can see the change in various efficiencies by changing the concentration of dopant, which is emitter. And our best result were achieved with emitter H2, which had the naphthyl groups attached to carbazole. And power efficiency was 9.3 lumens to watt, 17.9, sorry, 33.1 current efficiency, and 13.7% external quantum efficiency, and over 2000 candles at squared meter luminescence. So I guess that's all from me. If you have any questions, go ahead.